We're now going to start in Part 5, which is one of the larger tomes dealing with radon issues. It deals with the protocols, and I think I've summarized the protocols in a fairly reasonable way that makes it easy to remember most of the details. Now, before we get into the text itself, I have asked a representative from the Pennsylvania DER, Mr. Bob Lewis, to come down and demonstrate to us the different types of equipment to which these protocols pertain. And I think after we look at the equipment and see how they operate, we'll have a better sense of why the protocols are written the way they are, and therefore they will be more easily remembered. So if we could move now to another studio to take a look at the equipment that Bob has brought over. It's a pleasure to have with me this morning Bob Lewis from the Pennsylvania Department of Environmental Resources. His office has been gracious enough to ask him to come down and demonstrate much of their equipment for doing radon measurements. So Bob, welcome to the studio. And I think the first piece of equipment you're going to show us is the Radolex EPERM unit.
Correct, yeah.
And so why don't you just show us
Thank
what
you very much.
here.
We're certainly glad to come up here and try to enlighten some of the radon industry and some of the techniques that are available to them.
Great.
This is the EPERM system, EPERM standing for Passive Environmental Radon Monitor. And it's basically a radon detection system as opposed to a working level type system. And basically the crux of their system involves this little chamber here. Mm-hmm. And all that basically happens here is you take this into the house, basically place it as the protocols, EPA protocols specify, and you open this cap as opposed like this. This is in a closed position. Right. This is basically in an open position like this.
Once it's open, now it's starting to measure the radon concentration.
Correct. Right. The gas in the air then is diffusing into this top here where there's some holes that you can't really see. Mm-hmm. The gas basically diffuses inside this chamber where it creates ionization in the air.
Right.
The second part of the system here is the actual electret itself.
Okay. Now I notice that this electret is black in color, effectively. Is that significant of anything?
That's not particularly significant at all, no.
Okay.
This electret initially has a charge on it. Mm-hmm. Mm-hmm. And before you make the measurement in the house, you use this, which is basically just a voltmeter here. Okay. And this is used to measure the charge on this device. Okay.
So this comes with a certain amount of voltage, what, 500, 600, 700 volts perhaps?
Correct. Usually starts out about 750 volts.
750 volts, okay. And what do you do? Just lay it right on the
Right, you can basically lay it on here. Probably first what you would do, however, in the office or the laboratory is you want to check out this meter by using some standards, which they supply to you also.
Okay, so that comes with the kit?
Correct.
Yeah, and my understanding is when you buy the EPERM, you can buy just the chambers, of course.
Correct.
And then you could send can I open this?
Yes.
Okay. And then you could send just these electrets back, and they'll read them for you.
I believe they do that also.
And they have a little, you don't have to sit in the whole chamber back, they have a little cover that
yes.
that you can use to send back. So you brought that too.
There is it.
Okay.
Which they would certainly recommend you to put on.
Oh yeah, right, right. And you don't want to touch the electret at all.
Definitely, this is very, very sensitive to touch or dust, for instance, also.
Right. So typically, when it's ready to send back, if you didn't have the electrometer, the voltmeter here, you'd just mail this back.
Correct.
Right. And they read it and let you know what the radon concentration.
Right. And as soon as you basically put this cap on, then your measurement period is stopped.
Right,
so
okay.
Then that'll be stable until they read it.
Right. But now, if you have the electrometer yourself, and you can buy that as part of a kit,
right,
then you can read these electrets on your own.
You can read them yourself.
And then determine the radon concentration right to the picocurie per liter, right?
Exactly. They give you a little handheld Radio Shack calculator that you can make a calculation on. You can do it by hand. You can do it in your personal computer or whatever.
Right, okay.
And it's basically just done by initially just taking the standards that they also supply for you.
Okay. And that's now these standards that are checked that the voltmeter is operating properly.
Correct. This has a specified voltage that they will tell you. So this will be maybe 230 volts, say. Okay. And you should put it on here, and that should be reading 230 or whatever the standard actually is.
Now, can we take this out of its case here?
Certainly.
Okay. And if I hold it like this, to activate the voltmeter, do I just push this lever down?
Correct. Actually, first we should take that off and just check the zero on this thing, which you do by basically placing something like that on.
Okay, so we have this here, and then, okay, and what do we get down to?
And you place, and then it basically shows a zero, and I would do it one more time also.
Okay, let me let it go off.
And then go down again.
Does it take a long time to go off?
No, that'll stay like that. You go.
Oh, I see.
You want to do that again so that you duplicate that measurement.
Okay, all right.
Now I try it one more time since you got a different value than initially.
Yeah, what did we get there? I can't quite read
2.
that. 2, okay. 2 volts.
Try it once again.
Okay. All right, so now we have a 0 and 2 2s.
Okay, try it once more.
Okay. Let me just maybe...
We had a charcoal. You might try that. Okay. Some of them do that. Some of them don't zero. Ours, for instance, at the office, it stays at 1.
I see, okay.
But that's not critical because all you're looking at is a difference in voltage.
Right, right,
So
right.
if it reads 2 now, you just want to make sure that it reads 2 when you bring your
you're
device
done.
back in
Right.
from the
Otherwise,
field.
there'd be 2 volts unaccounted for.
Right,
Right,
correct.
okay, okay. But, all right, let's assume that it reads consistently 2.
Correct.
As it has started to do now. Okay, so now what do we do next?
So then you basically would put the standard on and make sure that that read as was specified in there when they
Okay.
sent it to you.
And what do we think it's supposed to be?
I don't know offhand.
Oh, all right. Well, I guess we'll find out just by turning
Right.
this on, right?
Which number is that?
This one is 833.
Well, it was 269, but that was in 590.
1990.
So
Okay,
it's
well, let's see.
probably lost some since then.
What's it reading there?
264.
264, all right.
So it's lost 5 volts.
It's lost 5 volts.
in
but
3
it's-
years. But it's been
okay.
3 years, so that's
Right.
understandable.
Right, yeah, that seems reasonable to me, too. Okay, okay.
So that basically just gives you an indication that the voltmeter is working correctly.
Okay,
And after you do that, then you can measure the actual devices that you're going to take out into the field.
okay, so now what would have happened is we take the chamber out into the field, and then we expose it
Correct.
by opening it up this way, and we leave it out for whatever number of days we want, and I understand there are short-term electrets and long-term electrets, right?
Right. The basically designation is most of the long-term ones, as far as I know, all of them are red with a red label here, as opposed to the short-term ones, which
Okay.
have blue labels.
All right. Can we see this label down here at all? I don't know if we can get, oh yeah, there it is. And I think you can see the blue quite clearly there. I'm watching it on the monitor, I can see that, that's blue. And the other one is in red.
Correct.
And one of them represents a short term and the other represents long term.
Right, and the basic difference that I'm aware of is just the thickness of the electret itself.
Right, right, okay. All right, so then, we finish the measurement in the building we're in, and we seal this, and then we pull off this electret, and we measure we just put it on here,
Correct.
like that, and then activate the voltmeter, and we read whatever the voltage, currently reading 403 volts
Right.
on that device. Okay.
And then you'll have a pre-measurement and you'll have a post-measurement. And then when you have those two measurements and you have the time difference, then you can calculate the concentration of radon in the house.
Right. So all you need then is the pre and post voltage and the amount of time that it was exposed.
Need the time. And there's one additional factor, and that's a background subtraction factor that they use.
Okay.
Gamma radiation, which this micro-R meter measures, can also interact, cause ionization in these chambers.
Right.
So that's something you should be aware of. And when they send you their kits, which is one very good aspect of the EPERM system, they send an entire notebook here. It has introductions and has their different products and prices and so forth. And also one very good aspect of that package is it sends you a quality assurance plan.
Okay. So it tells you how to operate the system?
Basically tells you how to operate it so you're getting accurate and reproducible results.
Okay. All right.
This is required, quality assurance plan, by the state. It's also required by the EPA in their radon measurement proficiency program.
Right, in the RMP.
So this is a
right.
big plus that many companies that supply this instrumentation don't have.
Sure, and this is no minor document.
Oh, no.
I mean, looking at this, it's probably 50 pages or so.
It takes quite a long time to write a quality assurance program.
Sure does, sure does. They've done a good job on that.
Yes.
Now, let's talk about the gamma radiation. The gamma radiation is, while it's not connected at all to the radon concentrations whatsoever, the gamma radiation is due to other sources of background radiation.
Correct. There's corrosion of soil and rocks and sometimes the building material of houses.
Okay, and typically, even if you don't know what the gamma radiation is, you do take it into account by standard background terms. In other words, you subtract off, I've forgotten the exact numbers, but I think it's something like 0.8
0.8 is correct.
picocuries per liter for every 10 microroentgens of gamma radiation. Is that right?
And they quote that in their manual.
They tell you how to subtract it off.
Yes, and it is state specific. So Pennsylvania has a certain value, Maryland has a different value, and so on and so forth.
Okay, oh, that's interesting. So the gamma radiation in different states, on the average, is expected to be different.
Right.
Right, okay.
Because of elevation and different uranium-bearing rocks and so forth.
Right. So even if you don't have a monitor of this type that measures gamma radiation these devices are still perfectly usable.
Still can give
devices.
you a very good measurement. Yes.
Right. Now, if you do have one of these devices for measuring gamma radiation, then you could use that instead of the standard terms.
You could use that.
they
You
give
would you would certainly get a slightly more accurate result. The difference would probably be not too substantial unless you were in a house that had very high gamma, 20, 40, 50 microarc per hour.
Right. And in that case, the problem may be much more than a radon problem.
Could be.
Yeah, right. Okay. All right. Well, that's a pretty simple system, and I did jot down some prices, and I think the EPERM unit is going to run somewhere around $2,800. I'm not exactly certain of that price, but it's in that order, and for that, I believe you do get a number of these chambers.
Correct. You get several of the chambers. You get the reader, the instruction manual, QA plan, standards. I think you even get a videotape that goes through
yeah, it shows you how to use it. Yeah, I have seen
that
their
nature.
video. Right,
Yes.
right. I just want to show one more thing. If we can take a look at this. When it comes to activating it, here we go. If it comes to activating, all that you do when you pull this little lever down is you just open the door so that the voltmeter measuring device becomes open to the electret. Otherwise, you see it's shielded and closed. Okay, so I just wanted to show that one extra feature. Okay. Now, gee, I do want to talk a little bit more about this. If we open this up at the bottom, I think you can see perhaps the plunger here. Can we get into this plunger at all? There, let me see here. Well, it's very hard to see. It's black and black, and but if I open this up, I think you can see there's a little motion inside, and the plunger moves back towards the top, opening the electret. The electret is covered by this. When this plunger is down like this, the electret is covered by the bottom of the plunger, which I'm afraid we are not able to get a particularly good shot on. And then there's a piece of filter paper that I see in there, Bob.
Correct.
Right? And what's the function of the filter paper in there?
Well, because this is a radon measuring device, you don't want radon progeny or the radon daughters to come in here and interfere with that measurement. So that filter paper basically will filter out all those progeny, and the only thing that allows is in there to diffuse in there is the radon gas itself.
Right. The progeny are all solids.
Correct.
And so the filter paper tends to subtract those out.
Solids, plus they're usually attached onto some sort of aerosol particle, smoke, dust in the air,
Right.
which is in this filter paper is very efficient at collecting those things.
Okay. So primarily you get just the radon gas or any other gases in the room.
Any other gases also,
into
certainly.
the chamber. Okay, that's great. All right, let's take a look at another piece of equipment here.
Or maybe just a couple additional things with the EPERM system.
Oh, okay.
Just some of their sort of side points is they have different detectors for different things. They have a range. This is a long-term range detector that extends the range of even their long-term red label farther.
Right. Now the red label is good for about a year?
About a year. Some people can make measurements for the year. That this, because of the reduced volume here in this chamber, you could go for maybe even a 2-year measurement if you wanted to, or if the concentrations were too high for this, that it would burn this electret out, then you might have applicability to use
Now, when you
this.
say burn the electret out, you mean lower the voltage on the electret down to below some value that's
beyond
useful?
the usable level, which I believe they quoted about 200 volts. Once it gets below about 200 volts, and you don't want to basically, you want to repeat that measurement.
Right. Oh, now that you've said that, something else occurs to me, and that is that you can deploy this detector into a home, expose it, and of course, you read the voltage before, say it's 750, and then after you've got it out for whatever number of days, you put it out maybe 10 or 20 or 30 days or whatever. You seal it up again, you read the voltage again, now it reads, say, 700 volts, that is, it's dropped from 750 to 700. You can use this chamber and electret again, is that right?
That's a very good point. Sure.
Starting off with your initial voltage of 700, maybe it'll drop to 600, and as long as the voltage doesn't get down around 200 volts,
200,
you just continue using this over and over again. So one chamber might be good for half a dozen measurements, perhaps a few more as well.
That certainly is one of the advantages of that device. It certainly also points out maybe one of the disadvantages, that if you happen to put a low or a short-term chamber in a high house, you would burn it out and then you would lose that measurement completely.
Oh, right,
and then you would have to go back in with maybe say a long-term chamber to do the measurement again.
Okay, right, yeah, so that would be a problem on the opposite side of the coin.
Yes.
Okay, and
some of the other things you can do with the EPERM systems, you can actually make radon and water measurements. Basically, they just use this. This is going to be something certainly more important when EPA finally sets their standard for radon and water, which we don't know when at this time.
Yeah, although I've heard 1996 is going to be a regulatory limit and that limit will be about 300 picocuries per liter.
That's the limit we hear on the grapevine, so I
Yeah,
don't know
right.
if it's going to sell.
Right.
And basically, you just, from the spigot, use this little vial here and fill that up, and then cap it, and then it's just,
This looks like a mayonnaise jar.
that's about what it is. You basically just put the vial in here, and the water spills over like that, and then you take one of your electrets with the E-perm chamber and put it in like that.
Oh, I see. There's a little
And
hook
it's
in it.
exposed in there.
Oh, no kidding. So then,
And like that. So basically the radon just off gases from the solution out of the water, and it exposes the electrode, and you can get an actual radon and water measurement by
I
this
see.
technique.
In other words, by knowing how much radon in air is in the chamber, is in this jar, which is monitored by the E-perm unit,
Correct.
we can calculate backwards, so to speak, into the radon and water concentration.
Yes.
That's a nice idea, nice feature.
So that's one of the things.
Feature. Yeah.
And something else that probably is not too applicable to most of the radon industry is they can make, with this sort of a prototype device of theirs, they can make thoron measurements.
Okay. Right.
We have not done many thoron measurements ourselves. Basically, the chamber is the same as these type of chambers, except they have cut some holes in here to allow the gas to diffuse in more easily to the chamber, since it has a shorter half-life than radon.
Right.
The applicability, once again, in the radon industry is probably not very great, but it is available.
Okay. Thoron being one of the confounding parameters of making a radon measurement. At the moment, it seems it would be pretty unusual for thoron to complicate a radon measurement, but that's always a possibility. And I think perhaps maybe a year or two, maybe a few more years down the road, we might see some protocols on how to deal with that kind of issue.
I wouldn't be surprised at all.
Yeah, but at the moment, I don't think there's anything that we are regulated to do in any case to sort out the thoron issue.
That's correct.
If it is an issue at all. Okay. All right. Is there more? This seems a quite capable instrument.
I think that's about it, at least that I brought from the E-perm instrumentation.
Okay. All right. Let's let's move on to another instrument now. Now, Bob, you've set up the Ludlam continuous working level monitor here, right?
Correct.
And this is for doing grab samples.
Yeah, this is not a continuous working level monitor. This is just
Okay.
based, okay. This
Right,
is just a
thanks.
scaler and a full multiplier too. This is a detector basically for looking at grab working level samples.
Okay, so here we're going to go into a house. This device is used to go into a house, take a few minutes sample, and then analyze that sample.
Yeah, typically we took about a 5-minute air sample in the house, usually in the basement, and then in about 40 minutes, anywhere between 40 minutes and 90 minutes, we could analyze the sample on here and have results within an hour and a half or so to the homeowner.
Right,
so
okay.
it's sort of a quick and dirty type of technique.
All right.
Probably not used very much anymore today because EPA protocols really aren't even allowing this to be used. But it was a technique that was used quite a bit in mines and also the homes when we were initially
Right,
sampling in the Reading Prong area.
Yeah, now you can't use it for the purpose of delivering to the homeowner a measurement upon which the homeowner will base whether or not to have mitigation performed.
Correct, you should not be doing that.
Right, but you could use it if you were a mitigator, for example, and you wanted to know if, gee, what's the radon concentration in a sump hole, for example. Maybe that's where it's real high.
It could be used for that. They probably use another technique we'll show later, more like just grab radon samples. It's much more applicable for that, but you could
Okay.
use it for that.
Okay. Well, let's take a look and see how this one operates here.
Well, this is basically just what they call a scaler here.
Mm-hmm.
This is all that just registers. This has a timing mode, and it registers the counts in here.
Mm-hmm.
And you can just basically demonstrate the counts by putting a standard into this. This is actually the detector here. This is a photomultiplier tube,
Mm-hmm.
and the actual detecting medium is zinc sulfide.
Right. So what happens is, typically what you would do, though, is you would go into the house and you use a pump of this type.
Correct.
And you draw air across. You have a.
We have a filter here.
Okay.
This is just the filter holder assembly here.
Right.
And you would place a filter in the filter assembly like such,
Right.
and this just maintains it in there.
Okay. And what we're going to do is draw air across that filter.
Correct. That's
and
what
then
that's what the grids are there for. That indicates where the aerosol particles are being deposited,
Okay.
so you know the correct position to place it in your detector.
Right. Yeah, you wouldn't want it upside down.
No.
Okay.
And just place it in there,
Mm-hmm.
and then just a matter of
Okay. We can probably hear that.
turning that.
Yeah. And so that will sample for however long we allow it to sample.
Correct.
Let's say 5 minutes.
So the air particles are just being drawn onto that filter as we
Right.
speak.
Okay, as we speak. And then after 5 minutes, we would stop this.
Correct. Just turn it off,
Okay. And
and then the filter just
Right.
taken out of there. And once again, it's critical that you place it this side up.
Yep.
So the alpha particles are traveling up towards the detector.
Right. So what we have on this now are actually the solids, so that would be the daughter products of the radon and not the radon itself.
Correct.
Okay.
And then you just basically close this, and the unit would just be turned on by pressing the count button.
Okay.
Now we're probably not going to see anything here because we didn't take anything, but we can certainly demonstrate that by placing a standard in here.
Okay. Now, if we were going to use this kind of device, what are the things we have to watch out for prior to turning it on in a building? Say prior to turning on the pump, the air pump.
Well, probably the two things you want to be doing with this is first you want to make sure you know what the efficiency of the unit is.
Right.
And you also want to know what the background of the unit is.
Okay.
Because those things are critical in the actual calculation of the radon daughter concentration.
Okay. Now we get the efficiency from this standard here?
Correct. This is just a standard. It's thorium-230, and it gives you a known amount of disintegrations per minute.
Okay.
So you basically place that in there.
And we should be seeing
count
some. Oh
this
yeah,
for-
we are. We're seeing some action now.
Oh, it's on. Okay.
I don't know. Can we get that? Oh yeah. I think you can just you can see the numbers running on that, and so we let this run
So
for.
we'll count this. We usually count it for 10 minutes.
Okay.
And we can get an efficiency for this unit.
Right. In other words, we would know, for example, the decays per minute on that particular one. I see it on the box is 10,900. So if we were to count for 1 minute and we counted, say, 5,450, exactly half of the decays per minute, then we'd say, well, the efficiency is 50%. We're
Right.
picking up half of all the decays are being picked up by the phototube.
And then that 50% efficiency then is used in the calculation to derive a radon daughter concentration for the house.
Right. I can see how that would work. And then now on that flow meter or on that pump, the things we would check when we turn it on.
That's a good point also. This should probably be checked before you go out in the field. Or we usually, I guess, check it just maybe once a week, just determine the correct flow of this.
Right.
We would use just a graduated cylinder and put a soap bubble through it and just time the soap bubble through a given distance or given volume. And by
Okay.
that you could get the flow rate of the pump.
Right, right. Now, the flow rate of the pump goes into the calculation
Yes.
that determines the radon daughter concentration,
Right.
the working level concentration. Okay. And now, but if I were going to use this myself, then to check the flow, I would simply turn it on, and I notice there is a flow meter gauge in there.
There is one there, yes.
And check to make sure that that is reading approximately the right value.
Right.
Right. Okay. Okay. And now, so one of the other things too is we want to make sure that we have a properly situated new filter in the filter holder for each case.
Certainly, you would usually use a separate filter every time you did a
Right. You have
actual
to
measurement.
discard those
Oh, yes.
filters. Absolutely right. Okay. All right. Well, that's a pretty straightforward system.
And this also can be used with a battery so that you can take it out into the field. We have done counting in the car, in vehicles, for instance, because we're out at, 40 miles away from the office. You have no time to get back to the office.
Right. Right. Yeah. At the moment, we have it plugged
We
in,
have
of
it
course,
plugged
but it is also battery
You have
operated.
to be somewhat careful. These cords can sometimes get a short in them, and if you're jostling it around while you're making the measurement, it's probably not the best idea.
So you got to stop the car to make the measurement.
Yes.
Okay. And this device, I noticed in my note here, this device, the scaler, the phototube, the scintillating material, and the standards run about $1,500. Is that about right?
$1,500 for
Roughly?
probably these two things. yes.
Okay. And again, these can be used for grab measurements, and they cannot be used to report to the homeowner what their radon concentration would be.
Correct. Since
Right.
it's just a snapshot in time.
Right. And we
It
know that
doesn't-
the. Go ahead.
Because of the fluctuations, obviously, it's not going to give you a very true representative value of the,
Right.
of the concentrations in the house.
Right. It's not much of an average value. It's a quick grab sample. Okay.
Certainly.
All right. Is there anything more
I
on
think
this
that pretty much
instrument?
covers this unit.
Okay, let's move on to the next unit then. All right, now Bob, this one here that you put up on the table, this is Eberline's working level monitor.
Right.
All right, and this one we would list as a continuous
This is
working level monitor.
continuous working level monitor.
I mean, we just let it run for as long as we tell it to run.
Whatever. This is basically the programming unit of the device. This is the detector here.
Okay.
So this is where
All
you
right.
do the programming, and you can run it for
Okay.
48 hours, which would be the minimum sampling
So I
time.
think you can see some of the controls here. I think you have this is the programming pad
That's the programming
here,
pad,
and this is
basically.
the output.
This is the output.
the data comes
This is
out
the
on it.
actual connection right here, where the reader interfaces with the detector,
Okay.
on-off switch, and that's about all there is to it.
Okay, all right, great. All right, and then, so it's a working level monitor. That means that, again, we're looking at radon daughters
Correct.
and not the radon itself.
Once again, you are collecting the daughters on piece of filter paper.
Okay, right.
That you're pulling through this detector
Right.
here.
In fact, anytime you're using a monitor with a piece of filter paper in it, principally, and you're going to look at the filter paper, you're looking at the daughters.
When you're looking at the filter paper, correct?
Right, okay.
The insides of the detector we can certainly show. I guess we should point out this is probably one of the more pricey models, but it certainly, for us, has proven itself to be very reliable.
Uh-huh. Okay, and the price is running about $7,000 for the complete
Right.
two-piece kit here.
Right. This is the actual air intake here.
Okay.
And the filter is basically placed inside here, and this has come down. This goes off. And there's no filter in there now, but we would just take this off and place a filter in there.
Okay.
And then when the pump starts, it would draw air through here and then onto the filter.
Right.
And then there's a solid state detector under here,
Okay.
which detects the alpha emissions from what's on the filter paper.
Okay. Now, so one of the things, of course, you have to be careful about in this is you want to replace the filter paper prior to each use, right?
It probably wouldn't be critical if you waited long enough, because it's going to die down. All these short-lived daughter products, within 4 hours, are basically going to be gone. The only thing
Right.
you would want to worry about is the filter paper becomes loaded and the flow is reduced, and you could have some problems.
Oh, I see.
So
Okay.
certainly, I always replace it every time.
Yeah, and I think that would be a
For
good...
the price of filter paper, there's no sense taking any chances.
That's right. Now, you also, this pumps air across the filter paper, and so there's a pump in there, obviously. Is there a way to check if the pump is having the proper flow rate?
Correct. That's one of the things that I do before. Two things basically is, once again, using the same type of standard, you can put the standard where the filter paper goes and
Okay.
run it through this interface here and check the efficiency of this unit.
Okay.
And you should also check the flow rate of this unit basically just by, this is the pull, that's the hook to the pump.
Right.
And you can hook this up once again to some sort of a calibrated device. We once again use the graduated cylinder
Right.
and determine the airflow rate.
Or you could just put it on a flow meter and get some
If
measure of
you
how...
had a calibrated flow meter,
Yeah,
you
if
could
you had
do
a
that
calibrated flow
also.
meter, okay, all right.
So those two things definitely have to be done because they enter into the calibration factor which you need.
Right, okay. And so now on the paper printout, you get an hourly report?
Correct. You'll get the start date and stop date and the serial number of the unit, and you get each hourly interval that you set it for, a concentration for that particular interval, and then you get an average for the entire sampling period that you've had it in the field.
Right. So you could use this to do a minimum 48-hour measurement,
Very easily.
right? And let it run. Oh, now this is an interesting thing. If you put this out in the house today, at this very moment, then it's going to take a little bit of time for it to get a reasonable sample on the filter paper. And the first few hours of data may not be indicative of the daughter product concentration in the building. So we have something called the ramp-up time.
Correct.
For a couple hours. Typically, what is the ramp-up time on a device like this?
I'm not sure what the ramp-up time is on this. I usually just throw out the first 4 hours of data.
Uh-huh.
So then I know that I'm into good equilibrium conditions.
Right, right. And then you run it, you'd like to run it 48 hours beyond that if you can.
Yeah.
Right.
I think
okay.
EPA allows you 2 or so hours if you want to throw a couple pieces of data away.
Right,
to still
right.
get your 48-hour, supposed to, meet their
Right.
R&B protocols.
Yeah, fundamentally the thing to do is if you know it's going to be 3 or 4 hours of ramp-up time, set it for 52 hours and come back after that. Then you know you've satisfied all the protocol requirements. Okay.
I don't know if we could get it to, we could try to interface it, and if there's any data in there, we could dump it or not.
Okay, so it has a memory in the detector part.
Right, because these things, basically, this would be placed in the field separate of this unit.
Right.
We've
right.
even actually mailed this. We've mailed it up to Andy George at EML to go through his chamber, for instance, and he's placed it, and you just have to time it correctly so that it goes off at the proper time, and he mails it back, and we can
And
pull
you
off the
then
data.
analyze it over here. Okay. Oh, I see. So it fits right on there.
It's right on there.
There's no cable connection there.
And then just turn it on.
Okay. And I
Takes
see
a minute-
something.
takes a
There's,
minute to
there's
sense.
also a little display here. I can't
Yeah.
read what that. Oh, it has the
It
date.
says connect working level monitor. So, oops, I know
Okay.
why. Let me just let's try this again.
Okay. I could hear the pump start up.
Yeah,
there for
it goes through a
second.
little self-check.
Okay, so now we're getting some data out
Getting
of
some
this.
printout.
Initial information.
And then there's just some different routines you can go through. It says set the clock. That's if the present time is not correct.
I see.
And then a parameter file, which enables you to set in calibration factors and flow rates and how long you want it to go for,
Right.
the total sampling time. And there's also a tail that they call it. This has the ability to check for thoron also.
Okay.
We set it for a 4-hour tail, and what it does is the pump stops, but it continues to look at the filter. And
Right.
it looks at the decay of the daughter products, and by that it goes to an algorithm that
I
can
see.
give you a percentage of thoron if there's any
Well,
present.
that's darn interesting. That's very, very clever.
But we'll see if we can get a printout. I don't know. Data readout, and then you just not enough data, so we lost it somewhere between the line.
Okay.
So-
All right. And so that's pretty much the whole thing.
That's basically it. Yeah.
And of course, it can be battery operated.
Yes, it has a rechargeable battery in it, and it also comes with a charging unit. You can, this charges it also here. This tells you basically when
Oh, I see.
your battery's 80% charged, or there's a
Okay.
separate unit you can just plug into at any outlet.
Right.
to
So
charge
it's a complete kit in these two small cases.
Correct.
Pretty much. Okay. And so the continuous working level monitor. We have the filter. Oh, and I know one thing I wanted to ask you. The determination of the calibration factor is. Do we do that every time before every measurement?
I honestly forget what the manufacturer says. I always did it. I always
okay.
checked the efficiency and the flow rate before all the measurements.
Right. It only takes a minute to do that.
Well, it takes a little bit longer than that. It takes maybe a half hour to do both of those two things.
Okay.
And
All right.
based on my measurements, you probably wouldn't have to, because every time I do it, it's always very consistent.
I see. Okay.
But I have just been, since we don't use it too much, it's easy for me to do it every time.
Right. Okay. Okay. All right. Anything else on this instrument that we should know about?
Not that I can think of at the moment.
Okay. Let's move on to the next instrument then. Okay. Now, Bob, you've set up the Pylon AB5 here, another active monitoring system. And before we get too far into this particular active monitoring system, I want to point out that if individuals are using active monitors, that they're required to get them tested in one of the government radon chambers, for example, down in Las Vegas or in, I was going to say Atlantic City, but not Atlantic City, Las Vegas or Montgomery, Alabama, right. And they have to do that every other year.
Every 2 years, active and or passive.
Right, but the passive ones, typically they can mail in.
They can send, yeah.
And that's only if they're a primary.
Correct.
If they're a secondary, for example, putting charcoal detectors out in a laboratory is doing the analysis, then the person who's putting them into the house but doesn't do the analysis does not have to send them. The laboratory does.
They don't have to send them, correct, but they will have to now take a test as of, I believe, next month.
Right.
Which is something a little bit new.
The RMP exam.
Right.
Right. Actually, we will have an issue on that very shortly.
Okay, that's good.
So, okay, why don't you tell us how this AB5 works here and what it can do for us?
Well, this is basically, I guess, the brains of the system. This employs the scaler, and this has the timer, and this is where everything interfaces into. And then one sort of nice thing about the Pylon equipment, you can just use a lot of different attachments onto this one thing to take many different measurements. You can take this particular, which what we have set up here. You can do continuous radon measurements with this, which is a passive detector. The gas just passively diffuses in here.
Okay, no pump in that case.
No pump at all. That's one thing I think we probably use this more than anything, simply because of that. We don't have to worry about any pump or flow rates or something. So it's very easy to use. You can use it with this method here, using a scintillation cell. With a method like here, it plugs into here. And you can use it in a continuous flow-through method this way, and then you do have a pump involved. You also have the working level capability here. This is a working level monitor. That's basically like the Everline unit we showed before, which once again hooks onto the front of this unit.
And then you put a piece of filter paper on that one?
Correct, full of paper.
Okay.
And you can also use it for making grab radon measurements, once again, using the scintillation cell. Instead of doing a flow-through measurement, you take this into the house, take your sample in here for 5 or 10 minutes, get a good representative concentration of the air or sample of the air, and then once again put it on here and you just count that sample for however long you want to count it.
Okay. All right.
We can certainly show each of those methods as you want.
Well, let's start with the using it as a passive continuous monitor.
Okay. This is one of the newer models here. There's just an on-off switch here. And it comes on. It goes. And they're basically things that remain programmed in here. There's a calibration factor in here.
Okay.
I don't know if you'll be able to see that. That's the interval length, which is you have a time base here for hours, minutes, or seconds.
Right.
And that's telling you there's 1 hour interval. That's the sensitivity of the unit, which is 1.49 counts per minute per picocurie per liter.
Okay.
Which you have to determine in a chamber somehow.
All right.
And then also in there is the background.
Okay.
0.83 counts per minute.
And that number that we determine in the chamber, that's what we go to Alabama for example, every other year?
Not really, no. You should be determining this factor separately. You should not be using the RMP program as a calibration for these units.
So those calibration factors have to be determined independently of the RMP program?
RMP would like you to do that.
Right.
A lot of people probably do that. You know, how incorrect it is, I'm not really sure.
Right,
I mean,
right, right.
you're measuring a known concentration, so you certainly could do that.
Right, right. Okay. How do you get that calibration factor? I mean, you have to buy some time in a radon chamber.
Correct.
And put the monitor out there
Right.
and then let it figure it out.
And then basically what you're doing, you're comparing counts per minute that this unit displays against the radon concentration every hour. So you
Right.
compare it every hours.
So in this case where we saw 1.4, it was actually 1.44, that was counts per minute per picocurie per liter?
Correct.
So that if it's in a concentration of 1 picocurie, let me see if I have this right, if it's in a concentration of 1 picocurie per liter, it's going to show up 1.44 counts per minute.
Theoretically.
Right,
correct.
okay, okay. All right, and then now how do you fasten the detector onto this device?
One thing also, this is one of the newer models here, that this couple different modes here, continuous, radon, rate, and quasi. We basically use continuous and radon. The older models just printed out just a raw number here, 100, 200, 1,000, or whatever. This will actually print out here or show in the display radon itself, so 25.6 picocuries per liter.
So right to the concentration?
Right to the exact concentration, which is sort of a nice feature.
Yeah, it does the calculation internally.
Right.
Right, okay.
That's why you have to have that sensitivity in the background in there.
Sure, right, okay.
So then basically this protective cap just comes off.
And what we have here is, this is a photomultiplier tube in here.
Correct, that's the photomultiplier tube in there.
Right, okay.
And then the this adapter just basically gets screwed on there.
Okay.
And then the passive detector, and you can see there that just has some zinc sulfide inside there, and
Right.
when the alpha particles interact there, they give off the electrons.
Right.
You go like that, and then you can just start-stop button starts it, and you can see the.
Okay.
You can see
And
the
so now air from the studio here is just diffusing into this Lucas cell of sorts, I guess.
Basically.
And as the alpha particles are emitted by the radon, then it's those alpha particles striking the zinc sulfide.
Interact with the zinc sulfide.
Right, and then that's giving off another particle that the phototube can pick up.
Correct.
And see, and those are the counts we're getting.
Right.
Is what the phototube sees.
Yes.
Right. Okay. All right. And there's probably ramp up time to this of a
Yeah,
couple
you're
hours.
looking
I
at
would
about,
imagine.
once again, well, this is about 4 hours. Takes
4 hours,
about
okay.
a half hour for the gas to fuse through this membrane, and then about 3.5 hours or something to come in equilibrium with the gas.
Okay. Right. Now in this one here, if we're using it in this mode for getting radon in picocuries per liter, the radon and its daughters are going to be in there. Is that right? Or is there a filter paper in there?
There is a filter,
Oh,
yeah.
I see it.
Once
Yeah,
again,
yeah, there is a filter in there.
That's a good point we should have
Okay.
mentioned. Once again, this is only looking at radon.
Just the radon, not the
Correct.
daughter products. Okay, right.
Yeah.
I didn't notice the filter paper on there initially.
All the scintillation cells would be doing the same thing, just looking at radon.
Okay.
And this would be the only thing that would be looking at the daughters.
Okay, all right. And so then the radon concentration pops out of this instrument,
Right.
right? Just like that.
And then what you can do is you can, at the end of your sampling, you can take this, basically this arrangement here into the field, leave
Right.
it in the house, shut everything down, bring it back into the lab, and just use this printer here, and the printer basically plugs into the back of the unit here.
Right.
And then you go through a little routine here, and you can dump your data out here.
Okay, so this actually has a memory in it, so it can remember all the data that it's been taking.
Remember, about 600 data points.
600 pieces.
So you could
Okay,
leave
that's
it in-
great.
You could leave it in the house almost a month if you wanted to.
Right, right. Okay, and now prior to using it in this mode, that is a passive radon mode, what kinds of things should we watch out for? Well, you have to check to make sure, would you check the calibration factor? You wouldn't check that.
We wouldn't check the calibration factor. We just do that basically once a year. The background, you may want to take a look at. It's a little bit more difficult to look at that because you have to find a low background environment.
Yeah.
What I primarily do is, once again, just put a standard in there.
Okay.
After it's calibrated, I run this standard for maybe 2 weeks every day.
Okay.
And then I get a range of, basically a mean and a range, plus or minus 2 standard deviations.
Right.
And I put this in there and make sure that the counts are within that 2 standard deviation value. Basically just tells me the electronics within here are working properly.
Okay, okay.
That's about the only thing that I go through
So
prior to
it's-
putting it out the field.
So in the passive, now you would call this what, a passive continuous radon?
Correct.
Okay, and so for that, it's really quite simple. You just put this detector on and really turn it on.
Basically, that's it.
And that's it. And then you calibrate it once a year, and you get it down to Alabama once every 2 years.
Correct.
To make sure that it is still running properly. Okay. Now, how do we, let's move it over to where we'd run it instead of passively, actively
Okay.
with a pump.
One thing, if anybody's considering buying this, they want to be careful about, you make sure you turn this off before you expose this photomultiplier to it.
Right, right.
Photomultiplier tube basically looking at photons, so it's very sensitive to light.
Right, and you can overwhelm it actually and
basically,
shut
yeah.
it down
Yeah.
for a while.
I've never experimented with that to see what happened, but...
Oh, I have.
Oh, you
I've
have?
done that in labs accidentally.
Oh.
And what it does is the tube becomes unusable for an hour or two.
But that
And-
doesn't ruin it or anything.
Nope, nope, then you just turn it back on and run it again. At least that's been my experience.
Okay.
Okay.
This is just basically an adapter for using these scintillation cells. The only difference in these two scintillation cells here is just basically the size.
Okay.
This has a little higher sensitivity. This is
Okay.
271 milliliters. This is 161 milliliters.
Okay, and the increased sensitivity is just due to the increased surface area
Right.
inside, right?
So this can come off. And this can go on.
Okay, so that's just a collar for adapter.
Correct. And then you can just hook a scintillation cell
Okay.
in there,
Right.
and you put the collar over to just
Oh, I see.
hold it
That
there.
holds it in place.
And then, actually, there's some tubing that would run back to the pump here.
Okay,
That
the
would be
pump's in
drawing
the
air
back.
in, but I won't
Right.
worry about that right at the moment. And then that hooks in there like that, so they're going
Okay.
to create a vacuum in here by the pump, and you will be drawing the air
So
through
air
here.
comes through here across
Once
the
again,
filter
through a
paper.
filter.
Now, in this case, we're not going to be looking at the filter
We're
paper.
not gonna be looking at the
So
filter.
this is just to block the daughters so that the only thing coming through is the radon gas.
Correct.
Okay. And then that gas would come out through another hose here into the back where
then
there's
just-
another pump, and then it gets expelled.
Expels right back into the room air.
Okay. Okay. So in this case here, now, is it important to change the filter paper before every measurement?
Once again, not critical as far as what's clean minutes on the filter. You just have to watch out for loading the filter.
Right. Make
So
sure
you-
that the filter still is allowing a flow of air.
Right. Once again, I think the same applies. Why not change the filter since,
Yeah.
well, actually they are expensive, but it's still worth it. Maybe this thing here would probably be, I don't know, $100, $200, something like that.
And how many filters do you get out of
I
that?
think there's probably 100 in there.
So you're talking it's about $1 to $2 a filter.
So actually, they're not cheap, really.
They're
I
not
guess.
cheap, no, that's right, that's right. Okay, now how can you check the flow rate on this?
Once again, you can use a graduated cylinder. You can use a
Okay,
calibrated
or a flow
dryer
meter.
or something like
Right,
that.
okay. Mhm.
I guess the advantages of these two types of things, either the passive or the continuous, is you can look, you can track the concentrations over time. You can look at the fluctuations, see what's
Right.
happening. We use these for lots of times diagnostics.
Sure.
When you see a heater comes on, you can see the spikes and so forth. You
Right.
get snowfall, something like that.
Uh-huh.
So it gives you a lot of data that something like a charcoal canister or some of these other devices,
Right,
like an
right.
e-perm, would not give you.
That's right, yeah, charcoal canister gives you one measurement, that's
One-
it.
one
A
measurement.
reasonable average over a given period.
Here you get
Right.
48 or 60, and you put them on your PC, and you have a very nice graph.
Right, right, okay. All right, and then, and this operates the same way you would do the start it
Right,
the same way?
everything else
and-
is the same, except you're just pulling air through.
Right, okay.
And
all
all,
right.
the other thing you could do is you don't have to have this on there. So that would be the continuous flow through. And if you wanted to use it in a grab sampling method,
Okay, yeah.
once again, you could basically work the same way here. And the
Okay,
air pump would be connected here, which we don't have it right there. And you'd be
right.
in the basement, and you just take a grab sample of radon.
okay, and you could grab for, how many minutes would you do a grab? Maybe 5 minutes?
We usually do 5 minutes.
5
Now,
minutes,
this is what you would certainly be using more so for diagnostics.
Right, again, you can't report that to the homeowner with
Right.
the intent of having some mitigation done.
Whereas if you wanted to do diagnostics, for instance, and you can put a tube on here, for instance, and then use this to go in different places that are inaccessible inside a hole that you've drilled in a block wall, down a
Right.
sump hole, anywhere you want, basically.
Now, let's talk about that, because suppose you use this initially and we go into a block wall, for example, and we draw off some air from inside the block wall to determine the radon concentration. Now, can I use that cell again? So I take the cell, I put it on here, and I get a number of counts per minute, or actually a radon concentration?
Well, you probably won't get a concentration. You'll just get raw counts is what you're usually looking
Okay.
at. in the sniffing type of mode.
Right, and all right, so then you might not even convert that to concentration.
You wouldn't have to, no, because you're just getting some raw numbers
Right.
when you're sniffing like that.
Okay, now would you then say, could I take the same cell and say, well, now I've drilled another pilot hole into the slab and I want to draw some air from out from under the slab. Could I use the same cell right away?
You could, but what you probably want to try to think to yourself is try to start with the lowest concentrations first, or where you might expect to see the lowest concentrations first. Certainly under the slab you'd expect to see very high concentrations.
Right, right.
So maybe I'd start in maybe just ambient and take a sample, because you certainly would have this cell contaminated.
Right,
If
and it
you
might
took a
stay,
high, and it might stay contaminated.
Right, and then so if you took a high one first, then you really couldn't use that Lucas cell for, that scintillation cell for a second measurement in short order. You might have to let that sit for a day or two.
It would very possibly overestimate, yeah.
Right, so you really ought to have 2 or 3 of these cells if you're going to
definitely.
go do some diagnostic
Definitely.
work. Right,
And you
okay.
also want to, you should probably flush them out in between measurements. Just go outside and flush it for 5 minutes or something.
Right,
And they come
right.
down. They come down pretty quick.
Yeah, okay, okay. And now, all right, now we have one
more, I guess.
more device. This pylon is also very capable.
Yeah.
I don't know if I mentioned, but this pylon device, I think with some of these accoutrements, runs about $3,700.
Now that would just be for this unit itself.
Oh, that's just this unit itself?
Yeah.
Oh, and then you pay more for the rest, for the other parts. Okay.
Everything's extra.
All right, so you're talking somewhere in the order of $4,000 and up to get this system operating.
And then the final attachment that we brought along here is just for the making the
Okay.
working level measurements. This, once
Right.
again, this would be a continuous working level, just like the Eberline. And it comes off, and a piece of filter paper is brought in there,
Okay.
and the retaining cap is put back on. And this is put in the exact same place that all the other attachments are put.
Okay. And then air is drawn through here?
Correct. Then you just attach a piece of tubing to there, and then to the back of the pump here,
Right.
and that would create the airthrow flue here, and the air would be traveling through there
Through here.
onto the filter
and then,
paper,
And then out.
and it interacts with the
Okay, now what's
zinc-
on, now what's on the filter paper? Oh, there's a zinc sulfide
zinc
inside
sulfide in
this
here,
portion too.
and that's in
Okay.
contact basically with the photomultiplier tube.
Right, so again, the filter paper has the daughters decay by the emission of the alpha particles. Those alpha particles strike the scintillating, the zinc sulfide,
Right.
and then the photons that come off from that are seen by the phototube.
Right.
Okay, all right. Now, one thing that I'm curious about, if we put the filter paper on here, the daughters are going to be collected on this side of the filter paper, and the alphas that are emitted, not all of them will make it through that filter paper, will they?
Probably not. It's very thin filter paper. I don't have any with me.
Oh, okay.
But you're going to obviously get emissions in both directions for
Right,
one.
right. And you're only going to get the ones that make it through that filter paper
Right.
and strike the zinc sulfide.
So, and once again, in this method also, an efficiency has to be determined.
Right.
There is a method that they give you where you actually plate out some daughter products onto a filter of exact same nature that you're using, and then you can calculate the efficiency by that method.
Oh, I see. And do they give you, I guess you can buy the source of the daughter products?
Yeah, there's a standard that they
A
give
standard you can use for that to get
Basically,
the efficiency.
I did not bring it along. You put a filter paper at the bottom of a little disc, and the daughters actually drop onto the filter
I
paper
see.
itself.
Okay, all right.
And you just take the filter paper out and place it in here and do a count. And
Okay, and that's how you determine the efficiency. Now, how often should you do that if you're going to use it in this mode?
I honestly forget that offhand. We very seldom use this mode.
I see.
We sort of favor the Eberlines.
Okay.
They're just seem to be a lot easier to use.
Right, right.
So I haven't done this measurement in such a long time. I don't remember what they're recommending for that.
Okay. All right, and in this mode here, it would be listed as a continuous working level monitor. Is that correct?
Correct.
Okay, continuous because we can let it run for long periods.
Right.
And working level because we're looking at the daughter products.
Correct.
And then we can get the data out 1 hour at a time if we want, plus some average value over the whole time period.
Well, this does not give you an average as the Eberline does, so you'll have to do that on your PC or the
Oh,
calculator.
I see, okay.
It just gives you
Okay.
the raw data, 25, 50, whatever.
Right, on an
43,
hourly basis.
On an hourly basis, or any time basis
Whatever
you want.
interval you set in.
Yes.
Right, okay, all right. This too has a lot of capabilities. Now, I think that's just about all of the equipment that you brought down for us, right?
That was all, with the exception of this one other monitor,
right,
this
right.
at ease monitor. And the only reason I basically bought this is because this is much lower in price than all these things we've been showing.
Right.
So for somebody, maybe mitigators or something that want to do something, they could certainly look at something like this.
Right, now I think this runs about $300–400, somewhere along that order. These other active monitors are running in the thousands.
All into the thousands,
Right,
yeah.
and this runs into the hundreds.
Correct.
Fundamentally. Now, how long can you let this operate if you put this into a house?
Well, this is a continuous radon monitor.
Oh, it's a continuous radon monitor.
Yeah, so you can
okay.
just leave it in, minimum of 48 hours up to whatever you'd like.
Right, right. And
And
then you were explaining to me earlier that if you read these little lights,
Yeah.
the little lights that you see here, somehow by
This is a little awkward for that matter. These lights will give you an indication depending on which one displays first,
Right.
the concentration. Some of their newer models actually have an LCD display up top.
which give you the radon concentration, right?
Yeah, there's two buttons. You can either press a present, I think, which gives you the concentration at now, or an average button, which gives you the concentration over the time periods you've been sampling
Yeah, it
from.
seems like that would be a little more convenient.
Quite a bit
Right,
more.
Right. Yeah, and I don't think that's a lot more expensive, actually. I still think that runs around $300-400.
I think they're a little bit more than that. I think they're more $700 or $800.
Oh, $700 or $800, okay.
And they give you
All
some
right.
printer capabilities too, which I
Oh,
think may
okay.
even plot your data out.
On a
Also,
regular basis.
I haven't seen the
All right.
newer models.
So this being a continuous radon monitor, does it have a pump in it when it's running?
No, just diffusion.
Oh, it's just diffusion and in through the top, apparently.
Correct.
Right. And I see there's a big piece of filter up here, some kind of fabric, actually. And is that used to prevent the daughters from diffusing through?
I'm not sure what that functions as, to tell you the truth. I don't know if that's you're using as a filter or not.
Yeah. It looks pretty porous. I don't know either.
Yeah.
I don't know either.
Um,
Okay, well,
we just basically have it. We don't really use it.
Yeah, yeah. If you want more details about the Honeywell monitor, you should contact the Honeywell people, I guess.
Certainly.
Okay, and I think that's about it.
I think that's about it, yeah.
Okay, great. Listen, thank you very much for coming and spending a good part of your morning with us. And I know you've got a good-sized drive back today as well. So, Bob, thank you very much.
I'm glad to be here.
Appreciate it.
Thank you.
You're welcome. Hopefully now that you've seen some of the equipment, these protocols will be a little more meaningful. So we start with our protocol considerations and a summary of those protocols. Now there are three parameters of interest that are discussed in the protocols. Well, at least the first two are discussed, precision and accuracy, and I've tossed in the one on bias because I think that's an important one as well. Now, as you see here in this visual, precision is the ability to arrive at close to the same value with several measurements. That doesn't mean they're right. It just means that the values are close to the same value. Accuracy is the ability to get the right answer. So bias is the effect of high precision. That is, you're always getting pretty much the same answer, but it's always wrong by the same amount. And that's what we call bias. Now, in this particular visual, I have seen this in earlier work. A bullseye is presented, and there are three sets of measurements that are made, each set being 4. Now, the measurements labeled O that you see here, you'll notice, are away from the bullseye by always the same amount. And we're taking the bullseye as being the correct value. That is, if the bullseye represents 10 picocuries per liter, that is the correct value. And you'll notice that the O measurements are always off by the same amount. Now, they have high precision because they're always about the same value, but they're quite a ways away from the correct value and always by roughly the same amount. And so the O's we would call high precision, poor accuracy, and positive bias. They're always a little too high. The way I've drawn it here, they're always a little bit too high in value. If you take a look at the B's, the B measurements, there are 4 of those, and all 4 B measurements are on the money. They have the right value. They're on target. And so those 4 B measurements have high precision because they're grouped together, and high accuracy because they all get just about the same value. If you look at the A's, there's one up here, down here, over here, and over here. These have crummy precision because they don't even reproduce the same value, and poor accuracy as well. They don't even come close to the bullseye. Now, the average of those 4 might come out to be an average value close to the bullseye, but that doesn't matter. We're concerned about precision, dealing with the grouping of the values, accuracy being getting into the bullseye, and bias, as we see in this example here. So the A's would be listed as, frankly, crummy all the way around. Poor precision, poor accuracy, and no reasonable bias either. They're just all over the place. Let's take a few examples of this. Consider 4 detectors placed in a radon chamber whose concentration is 10. That is, we know the chamber is set to 10. And suppose we get the values listed here. 15, 15.1, 14.9, and 15. Now this is high precision because the values are all close together, but low accuracy because they're 50% away from the correct value. And a positive bias. They're always to the right. They're always a little bit on the high side. So positive bias. As another example, numerical example, if the values were 9.9, 10, 10.1, and 9.8, now notice this is high accuracy, assuming the chamber is set to 10. This is high accuracy, high precision, no significant bias. One final numerical example, if the values are 11.4, 11.5, 11.3, and 11.5, as you see here, then this is positive bias. Remember, the chamber is set to 10, so this is a positive bias, always a little bit too high. High precision, those values are all close together, and fair to modest accuracy. They're all about 10 to 15% off, so that would be fair accuracy. So that's the distinction between the three terms that I would like you to remember. If you'll take a moment now, what follows on the next page is a set of questions, and if you deal with those questions as we have in the past, return to the video at this point. Again, I hope you've gotten all the right answers to those questions or worked your way to the right answers. Let's take a look at some information that is true in general for all of the protocols. In this visual, you see, in general, the minimum measurement time is 48 hours with a 2-hour grace period. Now, the purpose for a 48-hour minimum measurement time is simply this, that we have seen earlier that the radon concentration varies tremendously from hour to hour and day to day. So to get a reasonable average over diurnal fluctuations, a 48-hour measurement is required. So if you put a detector in at 10 o'clock this morning in someone's home, you can pick it up at 10 o'clock 2 days later. But suppose 2 days later you go over there and it's 9 o'clock. Oh, well, what are you going to do? You're going to wait around for an hour to pick it up? So that'll be 48 hours. The answer is EPA says no, you don't have to. They're going to give you a 2-hour grace period. So you can pick it up as much as 2 hours earlier. So you might think, so the minimum measurement time is 46 hours. That is not true. The minimum measurement time is 48 hours, and there is a 2-hour grace period. Furthermore, we see on this visual that short-term measurements should always be under closed-house conditions. Now, closed-house conditions, again, we've discussed before, should be done for 12 hours prior to the measurement and also during the measurement. This is true in all the protocols. If you're going to do a short-term measurement, this is required. Now, there are a few specifications and some wording that is important here. Measurements lasting less than 4 days must be closed-house conditions, must be made under closed-house conditions with that 12-hour requirement before and for closed-house conditions. And, of course, closed-house conditions must exist during the measurement. However, for measurements between 4 and 7 days, it is strongly recommended that we have closed house conditions for 12 hours prior and during the measurement. So for between 4 and 7 days, it does not say must, it says strongly recommended. Now that, in a sense, makes sense. That is, if you have the longer the measurement, the less impact the first 12 hours are going to have anyway. And so the shorter the measurement, the bigger the impact 12 hours prior to beginning will have. So I think you'll need to remember this, that if it's less than 4 days, that you must have 12 hours before. If it's between 4 and 7 days, then it's strongly recommended that you must have closed house conditions for 12 hours prior and before. Now, what kinds of things can operate when you're doing a measurement? Again, this is true for all of the measurement devices. It's okay to operate ear-to-ear heat exchangers, permanent radon mitigation systems. The idea being that these things should be operating in the typical daily activity of that house. It is, however, not okay to operate attic fans, window fans, if you had a whole house ventilation fan, those things were not okay to operate. Again, continuing on with the protocols for all measurements, the measurements should not be done if you're going to do a 2 or 3 day measurement that is relatively short term, and I have to say this is the majority of measurements, 2 or 3 day measurement, you should not do it if the winds are more than 30 miles an hour. That's a key number, 30 miles an hour. You want to underline that. The reason being, of course, high winds cause low pressures, and that enhances the amount of radon coming into the house, and that would give us anomalous values for radon concentrations. That is not indicative in any way of an annual average. And you should not perform these short 2 or 3 day measurements in rapidly changing weather. Again, rapidly changing weather means a rapid change in atmospheric pressure. Obviously, you cannot make these kinds of constraints on longer term measurements. If you're going to do, say, an 80-day measurement, which is still considered short term, anything between 2 and 90 days is short term. If you're going to do an 80-day measurement, you have no control over the weather or the winds, and no way to determine whether or not the weather or the winds are going to be greater than 30 or low atmospheric pressure conditions. So this is only for 2 or 3 day measurements. Also, in each of the protocols, closed house conditions must be verified. Must be verified. I underline that. And the reason, now what that means is somewhere in your log of what you have done at that particular house, you must write down that when you left that house, the closed house conditions were met. Or were not met, perhaps. Bearing in mind, of course, you're supposed to make sure that they are met. But that must be logged, that must be verified. Also, in all of the protocols, no measurement is to be 20 inches above the floor, less than 20 inches above the floor. All measurements are to be at least 20 inches above the floor, regardless of the detector type, whether it's the charcoal canister, the E-perm, etc. Regardless of that type, the location must be at least 20 inches above the floor. And we've seen this before, not near drafts, not within 3 feet of windows or other potential openings. Now, remember, potential openings. This could be things other than windows. It could be fan outlets for bathrooms, kitchens, etc. Not near high temperatures or humidities. These things, these locations constraints are true for all the protocols, for all the devices. Here's one you will never forget now, at least 20 inches above the floor. You've seen this 3, 4, 5 times so far. If the device is hanging, and you can hang devices like E-perms, Alpha Tracks, potentially you could hang a charcoal can, although they're generally not designed to do that. If it's a hanging device, it's to be hung 6 to 8 feet above the floor. The idea here being that it should be in the breathing zone. Now, this will be in the breathing zone, of course, if your height is 6 to 8 feet. Now, I'm not 6 feet tall, so 6 to 8 feet would never be in my breathing zone. Nevertheless, the protocols state that if it's a hanging device, that it's to be 6 to 8 feet above the floor, and at least 4 inches from other objects. Now, you want to keep it from other objects, away from other objects, because you want a sample of the ear in the room. And if you put it between 2 books, for example, then you'll only get a sample of the ear between the books, and that ear will not be exchanged as readily as the ear in other parts of the room. So at least 4 inches from other objects. In the area of documentation, what kinds of things do we need to write down? Now, if you just think to yourself, what things should I write down when I bring the detectors into the house? Well, obviously, start and stop times. You have to know this. For every device, you must know the start and stop time, as when you deployed it and activated it, and when you picked it up and stopped it from being active. You must also document whether or not standardized conditions were met. That is, did you have closed house conditions for 12 hours prior, if that's required? Compliance with standardized conditions. The exact location of the device. Now, you might think if you drop it off in a house that you'll remember where it is. But if you drop off 5 or 10 in a given week, and you pick them up early the next week, I think you'd like to know exactly where you put it. And was it on top of that file cabinet in the basement rec room, or was it on the coffee table in the living room on the first floor? You should write that down, where it is, where the location is. What other things should you know? If you think about this, the other things you should know the serial number, because lots of laboratories will report values based on the serial number of the device. So you're going to have to relate that serial number to where and in which house that was placed, and the manufacturer of the device. This you might not think you need, but the truth of the matter is you do need to remember it. Now, also other information should be jotted down in your log. And that other information, for example, whether or not there's a crawl space or a basement, the condition of the basement or crawl space vents, and the operation of any air-type devices. Is the individual running, say, a wood stove or a coal-burning stove that vents a lot of inside air to outside, depressurizing the building? These things that we have looked at so far are common to all of the measurement devices. And having said that now, the next page in your book is again a list of questions, and I'd like you to deal with those questions right now as you have in the past, and again return to this part of the video. Hopefully you again have gotten all the right answers or worked your way through the right answers. Let's move along through the protocol summary now and discuss the considerations called quality assurance. As you can see in this particular visual, the purpose of quality assurance is to give confidence that the results that you get have good accuracy and precision, and good precision with no bias. That is, you want to do the same things the same way that work over and over again, and you want to check to make sure that it continues to work. Now, one of the things that you need to check are called instrument calibrations. These are predominantly for active systems. For example, if you're using a grab sample device, or with a photo tube and some other lab equipment, for example, or if you're using an EPERM unit with a voltmeter where you're going to measure the voltage on the electret. For any of those things, you're to get the instrument, the laboratory component, in this case it would be the voltmeter, the electrometer, you're supposed to check that at least once a year, and that's what you see listed here in this visual. Instrument calibrations once a month, once every 12 months, excuse me, once every 12 months. Once a year. And that really is a minimum amount of time to make sure that the thing is still working right. And also note on the visual, I point out that the RMP program, for those of us using active systems, RMP program does not qualify as a calibration measurement. Now, the RMP program is where you take your electrometer or you take your laboratory equipment down to one of the radon chambers that the EPA has, and you show them that you can come up with the right result. Now, you would think that that could be used as a calibration, but currently the EPA does not permit that to be considered as a calibration. So remember that the RMP program does not qualify as a calibration technique. Now, there are three other things here: spikes, 3%, dupes, and on the next visual we'll see blanks. But for now, let me just talk about what a spike is. Part of your quality assurance, part of your procedures which will assure you that you're getting correct results, is to perform these spikes. And of course it points out that the spikes are to be done at 3%. And that's 3% per month. So if I'm using charcoal canisters, for example, and I put 100 of them out in a given month, I have to spike 3 of them. That is, they don't go to the home. What a spiked is I take the canister and I send it to a radon chamber. And at the chamber, the concentration, of course, is known. Suppose it's 20 picocuries per liter. And we put it in there. And then after the appropriate exposure time, that's sent back to the lab. And the lab should come up with the right answer. In other words, you're checking to make sure that the process works. And of the spikes, you're to do, as you see, 3%, that's per month, 3 out of every 100, with a minimum number of 3 per year. So even if you do none in a given year, you must still do 3 spikes, and you must do a maximum of 6 per month. So if you're doing, let's say, 600 in a given month, 3% of that would be 18. But you don't have to do 18 spikes, you only have to do 6. Now you're going to see this for just about every device protocol. Spikes are done at 3% with a minimum of 3 per year and a max of 6 per month. Another component of your quality assurance is going to be duplicate measurements. Now, in a duplicate measurement, what you will do is you go to a home, and instead of deploying one detector, again, if you're using charcoal cans, instead of deploying one can, you'll put two cans side by side. That's a duplicate measurement. You treat them identically, you send them back to the lab. And the duplicate should be done 10% of all your measurements on a monthly basis, or 50 per month, whichever is smaller. And this is nice of the EPA in the quality assurance plans, that it's always whichever is the smaller. So it's 10% or 50 per month, whichever is smaller in duplicates. Also, you're to do routine instrument checks, as you see here. Now, depending on the instrument you use, routine instrument checks are different. If you're using, for example, a continuous working level monitor, as we saw earlier, there's a filter always. Well, a routine and a pump, typically. And so in a routine instrument check there, you want to check the pump, check the flow rate of the pump, change the filter. And if you think physically of what actually goes on with that instrument, you can think through what these instrument checks should be. Also, as part of your quality assurance, you will do background measurements. And in this visual, let me go right to field backgrounds for a moment. We'll come back to the others in a second. If you look at field backgrounds, this too belongs to the technician. And what a field background is this. You will take your charcoal canister, again, if that's what you're using, you take your charcoal canister, and instead of deploying it out in the building or out in the field anywhere, you're simply going to send it back to the lab. It's a blank. It's never been used. And so the lab ought to return a value below their lowest level of detection, below their LLD. And typically for charcoal cans, that is 0.5 picocuries per liter. And so they should return a result lower than 0.5. If they returned a result of 2.4, that would tell you there's something wrong in the system. Either the charcoal can was not properly sealed, or their laboratory is not working properly. In any case, dupes are to be done at the rate of 5% on a monthly basis, or 25 per month, whichever is smaller. Now, if we think about this for a moment, we have spikes at 3%, dupes at, field backgrounds at 5%, and dupes at 10%. How are we going to remember this? Well, the way I remember this is this. The spiked ones are going to cost money. You're going to have to rinse space in a radon chamber. And so the percentage required is small, 3%. Blanks you have to pay for as well. You still have to pay for the detector, but you don't have to pay as much as renting a radon chamber. So there the percentage is a little higher, and so for blanks we're talking 5%. Dupes are measurements placed side by side, duplicate measurements, and they check, of course, on the precision of the lab. Those, at least you're getting some money for that, because when you deploy them, you're getting paid for at least one measurement. And so that, the percentage is made higher, 10%. So it's 3, 5, and 10, and I think if you remember which ones cost more, you can pick out which ones go on to 3, 5, and 10%. Also recognize that that's a total of 18% of all your measurements are for your quality assurance out in the field. And that sounds high initially, but I've conferred with a number of laboratories, and the labs tell me that their quality assurance plans generally require that 30% of all their measurements are part of their quality assurance plan. Effectively, every third measurement they do is part of their QA plan. So this 18% is not excessive in that light. Now, if you're using continuous monitors, the number of background measurements you should make should simply be a statistically significant number. Now, what that means is, to some degree, unspecified, and so simply a statistically significant number. I'm not going to give you a number by which you can guide yourself. Ask the manufacturer of the device, what's a statistically significant number? For passive detectors, in the lab, the laboratory has to check its own background. How many? A statistically significant number, again. So you'll want to remember that laboratories must do blanks. They're called lab blanks, a statistically significant number of them. If you're using continuous monitors, again, a statistically significant number. But out in the field, the number of blanks or field background measurements is to be done at 5%, or 25 per month, again, whichever is the smaller. Now, I'm going to summarize the protocols here for you to some degree. And in the area of results, there's a parameter called the LLD, the lowest level of detection. Now, what that number represents is that the laboratory is confident, or reasonably confident, that down to some low value, they are still reading correct values. For example, if you take a look at the EPERM, if we deploy this in a 50 picocurie per liter environment for a given amount of time, the laboratory will be able to read that pretty easily. And you'll be able to calculate it using the electrometer, for example, quite easily. If we lower the concentration to 1 picocurie per liter, can you still read that easily? That gets a little more challenging. What is the lowest value that we can read, say, with the electrets here, and still be quite confident? Well, we're told, as you see in this visual, that for electrets, the value is between 0.2 and 0.3 picocuries per liter. So they can read down to this level with confidence that they're getting the right value. Activated charcoal, that is the canisters, can read down to 0.5 picocuries per liter. Typically, except for these two and one other notable one, typically LLDs are less than 1 picocurie per liter. Almost every device can read to less than 1 picocurie per liter. Now, one other device which is unusual in some respects is the grab working level device. And we saw that operate in an earlier part of the video with Bob Lewis from the Pennsylvania DER, who showed us that. And they have an ability, those have an ability to read down, as you see here, since they grab working levels, 0.0005 working levels, which at a 50% equilibrium ratio is equivalent to 0.1 picocuries per liter. So they can read down to what seems to be about the lowest value available. But don't forget that grab working levels do not satisfy the constraint of the 48-hour measurement period minimum. Let me say one more thing about that 48-hour minimum while I'm here, and that is you can make measurements less than 48 hours, but you're not permitted to report those to the homeowner with the intention of the homeowner using that data to decide on whether or not a mitigation system should be installed. You might use a grab working level monitor, for example, to determine whether or not a particular part of a house has a lot of radon in it, maybe a sump hole that may have maybe the source of the radon in the house. You can do grab working level measurements for that. You just can't use excuse me, those kinds of results to give to the homeowner to determine mitigation systems. I want you to remember the minimum measurement period is still 48 hours, 2-hour grace period. Minimum is 48 hours. These very short-term measurements can be used for diagnostics, and fundamentally that's about it for the use of the short-term measurements. Coefficients of variation. Here, continuing on with this visual, coefficients of variation, typically they are at 10% at 4 picocuries per liter, which again at the 50% equilibrium ratio is 0.02 working levels. Now what this means, what is a coefficient of variation? Well, there's a fairly cumbersome formula that you can use to determine a coefficient of variation, but fundamentally, to a reasonable degree, if I put two duplicate measurements out, they should be within 10% of one another at as low a concentration as 4 picocuries per liter. So if this gets a concentration of 20, and the next canister right beside it, that other duplicate, that other part of the duplicates, reads 19, this is 20, that reads 19, they're within about 5% of one another. That satisfies the 10% requirement at 20 picocuries per liter in that case. And that same kind of close value relationship between the two duplicates should exist at 4 picocuries per liter as well. Now what I would like you to do is the next thing that follows in the packet that you have in the visuals is the table that I have summarized all the protocols with. And I want you to spend a few minutes just looking over that table, noting the percentage of spikes, dupes, and blanks that are supposed to be done for each different device type, And note the comments that have been made under the column titled Other. Things, routine instrument checks, etc., etc. And just spend a few minutes looking over those things and see if they confirm the information I've already given you. And of course they will. But that will help reinforce it in your mind. After that, you will see a host of questions. And I'd like you to answer those questions and then return to the video at this point, and I'm going to demonstrate a few of the calculations that are performed in determining radon concentrations. Okay, so if you'll do that now. Again, hopefully you'll have looked through those questions and gotten many of the right answers. Now, I want to present to you three different calculations which allow us to arrive at radon concentrations. And while I personally have not seen them on the written exams, does not mean that these kinds of calculations might not be on there. However, I don't want to stress too heavily that you should be able to do these. But there are some comments I want to make about the calculation which I think will offer some physical insight to you into how the device works. And that information hopefully will serve you well. Now, the first calculation I want to demonstrate is the one that is used for determining radon concentrations when you're using an electret, such as this EPERM. Remember, what you do is you simply open up the EPERM, you expose it for a prescribed number of days this way, and when you're done at the end of the number of days, you close it up. Of course, you will have read the voltage on the electret before you deployed the detector, and again, you would read the voltage again. We saw that earlier on when we were looking at instruments. And so the information you get typically is the kind of electret system you were using, and the voltage difference, and the number of days exposed. So let's take a look. For example, if the voltage difference here that we get in a particular exposure were 70 volts. All right, that's the difference in the voltage. And let's suppose the number of days that it was exposed was 4.2. Now, the concentration is calculated with the following equation, that the concentration is equal to the voltage difference. Now, you should be writing all of this down, divided by the time exposed. I guess we should extend this a little bit, times the calibration factor, which the manufacturer will have to give you, minus some background. Remember, we talked about background being the gamma radiation that strikes the detector while it's deployed. The calibration factor for this particular EPERM unit that I'm holding in my hand here, the calibration factor I see is 2.2. So let's calculate the concentration then. The concentration is the voltage difference, which is 70 volts, divided by the time exposed, which is 4.2 days, and again, the calibration factor, which is 2.2 in this case. And I'm going to worry about the background in a minute. So I just carried along with me. Now, 4.2 times 2.2 is 9.24. And then again, we still have minus the background. And so 70 over 9.24 is 7.58. Let's call it 7.6 minus the background. Now, so the concentration is going to be 7.6 minus a certain amount due to background. In other words, the background gamma radiation is what has contributed a little bit to this voltage difference. Now, how do we deal with that? Well, what I'm going to do here is just repeat what I've got on that first page and write down the concentration. This is what we just had, is 7.6 minus the background. Now, how do we determine the background? if you will recall, depending on the chamber type that you're using, depending on this particular chamber, and the manufacturer will tell you which one you have, you're going to subtract off a certain amount for the gamma radiation that exists. Let's assume for a moment that we have, if we have 10 micro-Roentgens per hour of gamma radiation, and what we're going to subtract, therefore, we're going to subtract off 0.8 picocuries per liter for every 10 micro-Roentgens per hour. In other words, we're getting 10 micro-Roentgens per hour, so we're going to subtract off 0.8 picocuries per liter. If we had 20 micro-Roentgens per hour, we'd subtract off twice this. And so our concentration then becomes the 7.6 minus the background, which is 0.8, leaving us with 6.8 picocuries per liter. And that's our resultant concentration. Now let me just return to the top of the calculation here to show you how the concentration is calculated. Again, if we look this over, notice that it depends on the voltage difference. The bigger the voltage difference, the bigger the resulting concentration. If you have a fixed voltage difference, for example, in this case, we had a 70-volt voltage difference, and it occurred over 4.2 days. Suppose we'd have had that same voltage difference over 10 days. The concentration would be much less, because we'd be dividing by 10 instead of 4.2. So you should recognize that the longer it's exposed for a given voltage difference, the lower the concentration you're going to get. That should make sense. It took longer to get the same voltage difference, and therefore the concentration must be less. And the background, of course, has to be subtracted, and I'm really just reiterating myself here. The background has to be subtracted, and again, depending on the chamber you're using, you're going to subtract somewhere on the order of 0.8 picocuries per liter for every 10 micro-Roentgens per hour, which in this case gives us 6.8 picocuries per liter. So the information you need to do the calculation clearly is the voltage difference and the time it was exposed. You must get the right calibration factor from the manufacturer, and you must subtract off the appropriate amount of background, as we have done in this example. Now, I've also added a few questions when we go on a little bit here, a few questions, and you will exercise yourself in this kind of problem. Again, not to make you an expert at doing this kind of calculation, but rather just to show you the trends of what parameters have what effect on the concentration. Okay? So now, let's go over to the second type of calculation that I would like to demonstrate. The second type of calculation I want to demonstrate deals with grab samples. And if you recall, in a grab sample, typically you will take a Lucas cell, and we've seen these, and they have, of course, the white scintillating powder inside, and we will, I'm putting the cover on it just to protect it, and we draw air into the vial. Sometimes we have a pump, and we pump air through, and so that we get the air in the vial in the cell, in the scintillation cell, to be the same as the air in the room we're trying to measure. And then we seal it off, and after it's sealed, after a given amount of time, we put it in front of a phototube, and the phototube acts like the human eye and detects how much light is being given off by the scintillation cell, and we count up the number of pulses of light. And from that, we determine the concentration. Now, in this calculation, which is a little more laborious than the one for electrets, we're looking again at a grab sample, and we are looking at the use of a scintillation cell. Now, the formula that is used is simply this, that the concentration is equal to the counts per minute of the sample minus, and again you should be writing this down, minus the counts per minute of the background divided by the efficiency of the system, and then corrections for time. And the corrections are a C divided by A, and then 1 over V being the volume of the cell that was used. Now, in this case, we have to get the background counts per minute. And the way we do that is we take the phototube with a fresh scintillation cell. That is, a scintillation cell which has been purged with nitrogen air or brand new, has no activity in it at all. And we put the scintillation cell in front of the phototube, and we count that up for a prescribed number of minutes. And we see so many counts per minute. Now, that's from a fresh cell. So in that fresh cell, suppose that the background came out to be, I'm choosing easy numbers for myself, 10 counts in 10 minutes, which is 1 count per minute. I choose easy numbers for myself, and then in the problems that you'll do, we'll make those a little more challenging for you. So we have a background of 10 counts per 10 minutes, so that's 1 count per minute, and that's the background here. Notice we do have to subtract off the background. Suppose now we take the Lucas cell, more typically called the scintillation cell now, in which we've drawn the air from the room, and we put it in front of the phototube, and we count up how many counts per minute we get from the ear sample. And suppose that when we do that, we get from the sample, suppose we get 1,200 counts in 120 minutes. That gives us, of course, 1,200 over 120 is 10. Note the ease of these numbers. Counts per minute. So now we have the sample count per minute, and we have the background counts per minute, a 10 and a 1 here. The efficiency of the system, that is the scintillation cell plus the phototube, you see for every picocurie of radiation you have in the scintillation cell doesn't mean you're going to see 1 count per minute using the phototube. And generally it's different from that. And in this particular case, the efficiency, at least for this example, is 4.62, and it's counts per minute per picocurie. What that means is that for every picocurie of radiation in the scintillation cell, the system of the phototube plus the scaler that adds up the counts, the system sees 4.62 flashes of light. Altogether, we see 4.62 flashes of light for every picocurie of radiation in the scintillation cell. That's what the efficiency means. So now we have this, this, and this, but we have not corrected for the time. And that's what the C and the A will do for us. Now the reason we have to correct for the time is because suppose that you left this scintillation cell in the back seat of your car. And if you leave it in the back seat of your car for a day or two, obviously the amount of radioactivity will have diminished. So we have to correct for that. And the correction factors are given in Exhibit 2-1, which I have on display over here in this visual. You also have it following, it should be the very next page in your workbook, and you see there are corrections for parameter A and a correction for parameter C. There's A right there and C right over here. And here's the time. Now A is the correction for radon decay from the time of collection, and you can see the rest of this sentence on your sheet, from the time of collection to the start of the counting the sample. Now in this particular example, let's let that time for, let me see, that's A, the time for A, B, let's let that be 4 hours. Okay? Time for it. Now that's the time that passed from the time I took the sample to the time I brought it to the lab and started the counting. Okay? So it was 4 hours from the moment I finished taking the sample and brought it to the lab for counting, or brought it to that instrument for counting. That's 4 hours. Now, if you look at the chart over here under A, under hours. And look at the time. Now just come down the time, come down to where it says 4 hours, and then sweep over to the value of A, 0.97026. So you just read it right off the chart, 0.97026. So A is 0.97026. And that corrects, when we place it into this formula, that will correct for the time it took for us to get it to the lab. Now, we're going to count this sample, not for just a few seconds. We're actually going to count this sample. In my example here, we're going to count it for a period of 2 hours. 2 hours. And that is, we're going to put it on this photo tube for a 2-hour period. And when we're done, we're going to look at the total counts and the total minutes, and we're going to get a counts per minute. And you can see it was counted for 2 hours. It's 120 minutes. So it was counted for 2 hours. Now, during that time, the count rate will drop off because some of the radon is going to be decaying. And we have to correct for that as well. And the way we correct for that is using this term C that you see right here. So you come down to the time, 2 hours, that's the count time, and you see C is 1.00757 because we counted for 2 hours. So in that case, jotting that down, C is 1.00757. We have everything in the formula now except for V, and V is the volume of the scintillation cell. Obviously, if we're working with a really big cell getting a certain amount of radiation, that concentration would be less than working with a little cell and getting the same amount of radiation. So the volume of the cell is important. And the volume of this particular cell, that volume is 0.17 liters, okay, about 2/10 of a quart roughly. And now we're going to take and plug all of these numbers into this formula. So let me rewrite the formula here. Again, we're looking at the concentration equals the counts per minute of the sample minus the counts per minute of the background. Always have to take background into account. Divided by the efficiency, and then we multiply that by C over A, and then again 1 over V. And I'm just going to plug in all the numbers now. The counts per minute of the sample was 10. The counts per minute of the background was 1. The efficiency of the system is 4.62. The correction factor C was 1.00757. The correction factor A was 0.97026. And then it's 1 over the volume, which is 0.17 liters. And so now 10 minus 1 is obviously 9, divided by, and I'm going to just do this division now, 9 divided by 4.62 is 1.95. So that's everything in here is 1.95. And then I can reduce this fraction, 1.00757 divided by 0.97026 equals 1.04. And so everything in here comes out to be that number. And then 1 over 0.17 is 5.88. And that is, of course, everything in this square brackets. And now if I multiply those three, I get 11.9 picocuries per liter. And so the calculation, as you can see here, we've done in a matter of 2 or 3 minutes. It's not particularly long. But note some of the things in the equation. The efficiency is the efficiency of the system. That's the number of counts per minute it sees per picocurie of radiation in the cell. Note where the volume of the cell is. It's in the denominator because we want to get picocuries per liter. So we want the liters downstairs in the bottom of this fraction. And so that's where the volume goes. And we do have to correct for the time, the total time. That is, part of that time, the C, is the time for the time that passes during the count period, that 2 hours of counting on the system. The A is the correction for the time it took to get it from the home to the sample, to the laboratory, in effect. So we have to correct for all of that in the calculation of a grab sample. And that's the way a grab sample would work. Okay? And again, I've got 1 or 2 problems following that I hope won't give you too much trouble, but I would like you to exercise your understanding of this equation in those problems in just a few minutes, and I'll let you know when it's time to do those problems, okay? In this third and final calculation I'd like to demonstrate to you, it's going to be based on the Kuznets procedure of determining working levels. Now, what that should tell you is if we're looking at working levels, we're looking at daughter products, which are solids. And so typically what we do in that case is we draw air across a filter, and then the daughters will collect on that filter, and we will then look at the radioactivity being emitted by that filter paper. So fundamentally what you have here is you have a hose through which we will draw air across a filter holder, like so, and then the hose continues on this way, and we draw air across the filter paper that's in here, and it collects the daughter products. Afterwards, we remove the filter paper. Here's the filter paper edge view, and we put it in front of a detector, and we count up how many, effectively, how many counts per minute we're going to get off of that piece of filter paper, and we're going to interpret that into daughter product concentrations, working levels. And the formula that is used is that the working level that we get is equal to the net counts, which we call C, divided by some coefficient, KT, divided by the volume of air that we drag across the filter paper, and divided by the efficiency of the system. And I'm going to talk about the efficiency in a minute. First, let me get this value C, and this value C is equal to the sample counts per minute minus the background. And to get the background, what we do is we take a perfectly clean piece of filter paper, brand new, and we put it in front of the detector, and we count it up for a few minutes. Now, in this example, suppose that the background gives us 3 counts, that is from a clean filter paper, in a period of 5 minutes. That is, we count it for 5 minutes, and during that time, we see 3 counts altogether. And of course, that is 0.6, 3 over 5, 0.6 counts per minute. So the background for this system in this example is 0.6. Now, the next thing we can get is the efficiency, and here, rather than the manufacturer telling us the efficiency, we have to figure it out ourselves, and that's a little more laborious. Now, remember, the efficiency is just the number of picocuries, the number of counts per minute the system will see for every picocurie or for every working level of daughters on the filter. And so what we do is, typically you get a standard piece of filter paper, if you like. And this is one way to do it. And suppose we get a standard that we know has 2,430 decays per minute. That is, on that piece of filter paper, let's assume that we have 2,530 atoms decaying every minute. We know what the decay rate, that's what the manufacturer who sold us the standard made it out to be. 2,430 decays per minute. And if we count this for 5 minutes, let's suppose that we get 5,985 counts in a 5-minute period. Now, we're not going to see all of these decays because, for one thing, some of the decaying products are going to come off in this direction. Some of the radioactive decays come off in that direction, and our counter's never going to see them. So we're going to see somewhere around half of them. And this example will make that come true. We have 5,985 counts. We put the standard filter paper on it. in a period of 5 minutes, and of course that comes out to be 1,197 counts per minute. Now let me just continue that here. You're getting 1,197 counts per minute. But not all of that is due to the standard. 0.6 of that is due to background. Now it's not much, I have to admit, but we're going to take it into account anyway. We have it. And so the efficiency, we can get the efficiency of this system is going to be, it's 1197 minus that 0.6 divided by the total number of decays per minute of the standard, 2430. In other words, we're not getting all of the 2430, we're really getting 1196.4 of the 2430 decays per minute. And if you work this number out, you get 0.49, almost half. That is, the efficiency of this system is 0.49. And in order to get that efficiency, you have to have had a standard available to you. And you must also have been able to determine the background earlier on. Now, let's further suppose that the sample volume, I'm looking at the V in the equation for working level now. Let me bring that down here. I'm going to look at this V for a moment. What is that volume? Well, that's the volume of air that we have dragged across this filter paper. And how do we get that volume? Well, the sample volume, we have a flow meter, and let's assume that it's flowing at 4.4 liters per minute for a period of 5 minutes. We let the flow occur for a 5-minute period, and if you do that, of course, you find that that is 22 liters. So the volume of air that we dragged across the filter is 22 liters. And now the final correction is the correction for time. That is, you take the filter paper off of the machine, you bring it over to the detector, and during that time some of the daughters decay, and if you remember, the half-life of the daughters tends to be pretty short. So we have to take that time into account. And that's what the KT factor will do for us. Let me just rewrite the equation here so we have something neat to look at. Again, the working level is, that's the net counts over KT, V, and E. And actually we have everything except KT. And for that, all we have to do is determine how much time passed between the time we stop the flow meter and remove the filter to the time we put it on the monitor that's going to measure the counts per minute off of that filter paper. Now, for this purpose, let's let the time between, and I'm going to explain this to you, be 45 minutes. Now what I mean by this time between, that's the time that passed from the moment we stopped the flow meter, or stopped the flow through the filter paper, that is from the moment we stopped taking our sample, to the time we put it on our detector. That's 45 minutes. And from that we can get the KT factor, and well, with one more piece of information. Let's let the count time, then we're going to count for 10 minutes. If the count time is 10 minutes, then even during this 10 minutes, some of the daughters will have decayed. So what correction do we use? What time correction do we use here? And if you look at the chart in the very next page, you will see that we have time listed here, and then we have the correction factors listed here. Now what time should we use? Well, we should use the time, the total time that passed from the moment we removed the filter from the sampler to the middle of this time period, this 10-minute period. That is, it was 45 minutes from the time we removed the filter paper from the sampler to when we put it on the detector, and then we counted for 10 minutes. That's an extra, halfway through this 10 minutes is an extra 5 minutes. So the total time is 50 minutes to get to the midpoint of the count time. And if you come down here, time 50 minutes, the correction factor is 130. And so now we have all of the variables that go into the equation KT is 130 to get the working level. So we get the working level. Now remember, this C is the net counts. And so what we have to have is, let me just write that as the sample counts per minute minus the background counts per minute, all divided by KT, which is 130, the volume, which was 22 liters, and the efficiency, which was 0.49. Now, when we still have to count the sample, I have not given you that information yet, but let's suppose that when we count the sample, when we counted the sample, that is, we put the filter paper on it, we counted it for that 10 minutes, let's suppose that we got 560 counts in that 10 minutes. So the sample is 56 counts per minute. And that's the number we're going to put up here in the sample. Background, we already know, is 0.6. So let me write this equation again here. The working level comes out to be the sample counts per minute, right here, which is 56, minus the background, which we determined to be 0.6, divided by the time correction factor, the volume of air drawn over the filter paper, and the efficiency of the system. Now 56 over 0.6 is of course 55.4, and divided by 130, 22, and 0.49, if you work that out, comes out to be 0.04, and so the working level is 0.04. Now that's a pretty ornate calculation all in all, because we have one difficulty, and that is we have to get the efficiency of the system on our own. It's not told to us by the manufacturer. I want to look at just one other parameter here that has an effect. And let's take a look at the volume in this particular Kuznets procedure. Suppose the flow meter were reading too low. Now I'm just considering this equation here. And if the flow meter is reading too low, that means the volume we get will be too low, regardless of how many minutes we run it for. And if the volume is too low, we'll get a working level that's going to be too high. And so the effect of the volume is very large on the results of the working level. And you need to recognize that, that the flow rate is very important in determining the concentration based on the Kuznets procedure. Again, there are a few questions and one or two calculations that I'm going to ask you to do, which follows this last calculation, and then return to the video at this point. So please deal with those questions as we have done in the past, and return back to the video at this point. We'll now begin part 6 of this program, and this part deals with the Radon Measurement Proficiency Program that the EPA has created and continues to support. Now the purpose of this program, as you see here, is to provide opportunities to demonstrate proficiency. This is so that those of us who are doing radon testing or laboratory work can demonstrate on a national level that we are quite competent at doing that. And also, the purpose of the program is to assist consumers and state agencies in finding people who can do these kinds of measurements competently. There are two kinds of measurement services that are allowed into the EPA R&P program. The first one is called the primary measurement service, as opposed to the secondary measurement service. And what distinguishes them is that in the primary measurement service, those individuals or companies that read or analyze measurements and yield results are called primaries. That is, if you're using a continuous radon monitor, whereby you actually get the radon concentration values right there, or if you're a laboratory analyzing charcoal cans, then and coming up with the radon concentration in picocuries per liter, then you are a primary. If what you're doing is deploying the detectors but not reading them to get the final concentration, then you will be listed as a secondary measurement service. Now we see here that primary measurement services are required to have a quality assurance plan. That is a prescription by which you do your measurements and come up with results. They will be listed by the EPA. There will be a long listing of individuals or companies who are noted as RMP proficient, and they're listed by device. Now what that means, if you're a primary, is that if you're using charcoal cans, for example, in this case I'm holding up a 4-inch can with a diffusion barrier that you may or may not be able to see. You could be listed, if you use this can, as one who uses 4-inch cans with diffusion barriers. You are specifically listed for that device. You're not listed for EPERMs. You're not even listed for a 3-inch can without diffusion barrier. It's specific to the device that you're using. And if you are a primary, you must be tested periodically in a radon chamber. Now, the chambers that are currently available for this are, one is in Montgomery, Alabama, and the other's in Las Vegas, Nevada. And some of the devices can be mailed in, others must be carried in by the operator of that device, which of course complicates the issue for primary measurement services to some degree. There may be other radon chambers to be opened up as the years go by, but currently the two available are in Las Vegas and Montgomery. And fundamentally what happens for primaries, again, suppose you're using charcoal canisters, is you would send 4 of these charcoal canisters down to the chamber, and for charcoal canisters, I believe you can mail those in. They're exposed into the EPA's radon chamber and returned to you. You analyze them, and you're supposed to come up with the right result, plus or minus 25%. And I'll talk about that percentage business here in just a minute. And so the idea there is that primaries have to be able to show their proficiency regularly in the RMP program by sending their detectors to the radon chambers. Now secondaries, as you see here, must use primaries to determine results, and they are listed by method. That is that a secondary service, that is the individual who goes into the home and deploys the detector or deploys perhaps an electret measuring device, that individual will be listed as a secondary because he does not come up with the result, the actual radon concentration later. But he is required, if you're going to be part of the RMP program, he is required to use someone who is a laboratory that's listed as a primary. That is a laboratory that has gone through the RMP program and shown that they can satisfactorily come up with the proper results. Also, the secondary is listed by method. So if you're listed by activated charcoal, the acronym for it being AC, then you can use a 4-inch can with a diffusion barrier. Without a diffusion barrier, you can use a 3-inch can. Any device that comes under the activated charcoal method and that has satisfied the RMP program through some primary lab. You're not listed by device, you're listed by method as a secondary measurement service. Now, further requirements of the secondary measurement services is you must have a quality assurance plan, you must use listed devices and listed primaries, that is primaries who have passed the RMP program. You do not need to be tested. Now, unfortunately, this does not mean you can skip the RMP written exam. It just means that you do not have to send your devices to the radon chambers in order to demonstrate your proficiency in coming up with the proper results. Now, how do you get into the RMP program? Fundamentally, you must file an application. And if you're a primary, if you intend to be a primary, you have to have one application per brand, model, and type of equipment. If you're a secondary, you need one application per method used. So if you're a secondary, all you have to do, and you're going to use activated charcoal, you just file an application that says you're going to use activated charcoal, ACs. And of course they know that means different kinds of canisters. And that's all your application has to comprise. That is just the activated charcoal. But if you're a primary that is coming up with the radon concentrations themselves or the working level values themselves, then you would be listed, you would have to have one application for 4-inch cans with a diffusion barrier. You would have to also have another application for 3-inch cans, for example, without a diffusion barrier. Or if you're going to use continuous working level monitors, let's say, and you're going to use the one by Eberlein and the other one by Pylon, then you have to have one application for the continuous working level monitor by Eberlein and a separate application for the one by Pylon. So you can see that for the primary, their application is by types, very specific type of equipment. For the secondary, it's by the method. Now, there are two types of requirements in the RMP program. The first of which is the continuing requirement. That is, if you're already in the program and you're continuing in the program, there are certain requirements. And there is a set of requirements in order to enter the program. There's quite a few of the requirements, actually, and I think I have a method by which you can remember most of them without getting too caught up in the whole issue of memorizing. You see here the entrance requirements. Obviously, now if you just think about it and use common sense, obviously there's got to be an application. You must have developed a quality assurance plan. Now notice this, develop and implement. Obviously you can't have implemented the plan yet, or you should not have implemented the plan, because you haven't gone through the RMP program yet, even as a secondary. So, but develop and implement, because the word develop is there, means since you must have a QAP, this must be part of the entrance requirements. Same for have and use your SOPs, standard operating procedure. Now the standard operating procedure is really a very practical application of your quality assurance plan. They're very closely related. You must, in all cases, comply with requests for information. If the EPA calls you or sends you a letter saying how many tests did you do this year rather, then you're to comply with those requests for information. That makes sense. Follow the EPA instructions. Gee, that makes sense. And if you're a primary, you must pass the radon measurement test, meaning simply that you must get your detectors through the radon chamber and come up with the right results. That's if you're a primary. Of course, you don't have to do that if you're a secondary. Now, those things hopefully make sense. And those are the entrance, some of the entrance requirements. In fact, I believe those are all of the entrance requirements. Now, for continuing requirements, I've listed those additional ones. You're to notify the Quality Assurance Control Officer at the RMP program of any changes. If you change your mailing address, for example, then you're to notify them that you have changed your mailing address. That makes sense. Again, develop and implement a quality assurance plan. Well, when you entered the RMP program, you already developed it. But because it says develop and implement the quality assurance plan, this becomes part of the continuing requirements as well. Same comment for have and use SOPs, standard operating procedures. And of course, you will follow the protocols. Anybody who's in the business is going to follow the protocols. There's a modest amount of protection in doing that. Further continuing requirements listed here. You will follow the EPA guidelines for advertising. You are not permitted, for example, to advertise that the EPA has certified you if you've passed the RMP program, because the EPA does not do certifications. There are only certain statements that can be made regarding advertising and quoting EPA. So you will follow the EPA guidelines. You will follow the guidelines in reporting results. And here, I want to point out to you that when you report your results on radon concentrations, for example, the house got 4.1 picocuries per liter. The guideline is to report 1 decimal point. That is, you're to report 4.1, not 4.16723, but just 4.1 picocuries per liter. So radon concentrations in picocuries per liter are reported to 1 decimal place. Working levels, however, since they're obviously much smaller, working levels are measured to 3 decimal places. So typically when you do a working level measurement, you will report them out to, say, 0.003 working levels, or 0.023 working levels. You will always report it with 3 decimal points. You will also, continuing on here, comply with requests for information, follow EPA instructions. If you're a secondary, you're to use R&P primaries only. And if you will pass the radon measurement test, that is, go through the radon chamber if you're a primary, periodically. Now, in the R&P program, if you're a primary and you send your detectors to the radon chamber, how many of them do you send? Well, typically, I note here, you send 4 of your detectors. If you're using charcoal cans, you send 4. If you're using EPERMs, you send 4. If you're using alpha tracks, you send 4. And you have to get all 4 correct. However, the ones that are exceptions to this, and I think these are not too hard to remember, the continuous radon, the collapsible bag, continuous working level monitors, and the RIPSU units, all of those, you have to send only one of these devices. In fact, in some of these devices, they're not allowed to be mail-ins. You actually have to bring them down yourself. And that makes sense that those would only be one, because how many of us would have 2 continuous working level monitors? They're a fairly expensive device. And so one is allowed in those 4 cases. Now, the way to get through the R&P program, again, if you're a primary, and we need to be familiar with this, if you're a primary, is remember you're sending in, let's say we're doing it with charcoal cans again, you're sending it in, you're sending 4 of them in. And the requirement is this, that you must be within 25% of the correct result in all 4 measurements. If you are, if all measurement errors are less than or equal to 25%, you will be listed. That's it. Effectively, the issue for you is over, at least for the year, until the next cycle comes up where you have to do it again. And remember, this again is only for primaries. Now, if all the measurement errors are not within 25%, in other words, no, the measurement errors are not within 25%, then the question is, are the measurement errors all within 50%? Now, if they're all within 50%, you can be retested. And in that case, you sure do hope that in the retest, as you'll see, that the final results are within 25%. Now, what retest means is that if you sent your 4 cans in and they're all within 50% but not within 25%, then you can resubmit 4 new cans. You don't have to reapply or go through all the paperwork all over again. You can typically resubmit in very short order the 4 new detectors to try to get within 25%. Now, if your measurement errors are more than 50%, then you've got to reapply to the program and start all over again in the application process, which, of course, is a fairly long, time-consuming process. Let's go on now with the area of assuming that all of the values that you got were within 50%. So you resubmit perhaps 4 new charcoal canisters. And now the question is, are all the measurement retest errors within 25%? If they are, then you'll be listed, and that will end the issue for you, at least again for that year. If not, you must submit corrective action and reapply from scratch all over again. So you have to go through the entire application process for the R&P program, including what corrective action you've taken to explain away the large percentage errors. Give you an example of this. Let's take a look here. Suppose you have measured values given here. In other words, all 4 detectors were put into the radon chamber at these different concentrations. In other words, these were the chamber values, 7.2, 18.3, etc. And you come up with values as indicated here. Note here the percent error in each case, 14, 10, 29, and 15. Now, this is suitable for a retest. It didn't pass because one of them is greater than 25%. If this one had been 25 or less, then this particular individual would have passed the R&P test. But because one of them, the 29%er, is more than 25%, this individual would be suitable for a retest. And hopefully during the retest, they would get within 25%. If not, in the retest, then they would have to restart the application process. As a second example, Suppose you send or you bring down a continuous radon monitor, and the target value that's put into a radon chamber at 35 picocuries per liter, and the measured value is 15.7. Here the percent error is 55%. As you see, not eligible for a retest, must reapply from scratch. Now you'll note on your very next page of your text there's an array of questions, and as is usual, I would like you to deal with those questions as we've done before. This will end part 6 of the program, but when you're done with those questions, you've checked the answers, return to this part, and we will continue on with part 7 of the program. This is part 7 of the program, and in it we will discuss the Radon Contractor Proficiency Program. EPA has a proficiency program for radon contractors, and pretty much most contractors in the EPA, most contractors doing radon mitigation will become part of this, or become members of this RCP program. Now, fundamentally, if we look at the standards required of the contractors, as I have listed here, the contractor is required to review and assess prior measurements. Now, let me just talk about that for a second. The reason the contractor is at the house to do a radon mitigation or give an estimate of a radon mitigation is because there's a measurement that indicates that it needs to be mitigated. Now, if you're in the RCP program, you're required to look at that measurement and see if it was done in accordance with the protocols. And if you suspect that it was not done in accordance with the protocols, that contractor will be required to recommend that the house be retested before mitigation begins. Doesn't mean the house has to be retested, but the contractor must recommend that it be retested. The RCP program also requires a visual inspection be done before the mitigation work be started, obviously. It's unreasonable for me to call a radon contractor and say, look, I've got a radon problem in my house, concentrations, let's say 10 picocuries per liter, and I'd like you to come down and give me an estimate on mitigating it. If the contractor says to me, okay, it's going to be $1,500, and we'll put a sub-slab mitigation system in, and we can start Wednesday. How would that be? That would not be very satisfactory to me. Reason being, the guy hasn't even seen the house yet. How does he know that that's going to work? That may well turn out that sub-slab will be the system to use, but how does he know that ahead of time? So a visual inspection, at minimum, is required for all of those who are taking part in the RCP program. The contractor also advises whether or not to use temporary measures. Now, in the case of temporary measures, you might go and someone's using a recreation room in a basement, and there are some windows, and the concentration in that room could be, let's say, again, 10 picocuries per liter. And you might suggest, well, look, we can't start until a week from Thursday to do the mitigation. What I recommend in the meantime is you leave the windows open, or maybe we put a fan in the window, something like that. So the contractor will be required to advise whether or not temporary measures should be used. However, as you see here on the last item on this visual, you may not use temporary in place of permanent measures. That means you can't say, well, put a fan in the window and that solves your problem, give me $300 and I'm out of here. That would be inappropriate, and it is not acceptable according to RCP standards. Furthermore, if a temporary system is to be used in some way, it must be labeled as temporary, as you see here. You have to label it as a temporary radon mitigation system, and that you have 30 days within which to install a permanent system from the time you install the temporary system. 30 days. So these are the kinds of things we need to remember for purposes of the RMP exam. It's interesting that the RMP exam, the Radon Measurement Proficiency Program, requires us to know something about what goes on in the RCP program. That is not unreasonable. We should know something about what the other individuals who dovetail into our measurement area are doing and what they're required to do. Now, again, in accordance with the RCP standards, that is, if you're going to be part of the RCP program, there is a requirement that you give the client certain kinds of information. and I have listed them here. You must show them your RCP ID number. If you're a member of the Radon Contractor Proficiency Program, you will receive a photo ID card with a number on it. The client is supposed to get that number. You're supposed to tell the client the entire scope of the work. That is, how much is going to be done, where will the work be done, if you're putting sub-slab in, where will the pipes be put into the slab, etc. The client is also supposed to be told a statement of any known hazards of the materials used. Suppose you're using some cement that gives off a toxic gas for 12 hours. The client has a right to know that, and the client should be told that. Further, the client will be told that you are, as a contractor, complying with the EPA requirements, and that you are complying with all the codes, all the suitable codes, local codes, construction codes, electrical codes, etc. Those are the kinds of information that the client is supposed to get. Beyond that, there's two other items that I think you should be familiar with that the client should get, and one is the client's to be told what the future maintenance is going to be. If you put a sub-slab system on it, maintenance may be the replacement of the fan after 10 or 12 years. Or certainly it will be to make sure that the exhaust port of the mitigation system is free and clear of debris and leaves and squirrels' nests, etc. Also, the client is to be given an estimate of the installation and the operating costs. The client has a right to know an estimate of what it's going to cost for the entire mitigation system installed and how much it's going to cost on the average to operate that, typically on a yearly basis. In regards to the system installation, let's take a look at some of the requirements that the RCP program puts on the contractor regarding system installations. Here you see temporary systems should be made permanent within 30 days. Actually, we've seen this already, clearly something you want to remember. The mitigator complies with all laws and codes. That makes sense. That's an easy one to remember. Now, these MSDS sheets, these are the material safety data sheets. They're to be given to all workers, and what they are is a list of the known hazards of the different products that are being used in the mitigation. Again, suppose you're using a caulking compound that should not touch your fingers, and if it does, it should be washed off in some way. That kind of information would be listed on these MSDS sheets, and that kind of information is to be given to every worker. Also, under system installation, the RCP program requires that a monitor must be installed, typically in a sub-slab mitigation system, in one of the rising pipes that comes from the slab and goes up and eventually ends up out of the house, guiding the radon gas out. Typically, a small hole will be drilled and a manometer will be placed in there with a colored liquid in it to indicate whether or not the system is under depressurization. These are just $3, $4, $5 items installed in a matter of 1 minute, and they're easy to put in. Monitors are required in accordance with the RCP standards. Further requirements in the standards is that every visible portion of the mitigation system is to be labeled as a radon mitigation system. So if you have, again, a sub-slab mitigation system, and you have 2 or 3 suction points and 2 or 3 pipes, every pipe is to be listed as a radon mitigation system. Also, there must be a central label placed on the system. Now, what central means to me could mean something different to you, but to me it would indicate that probably by the circuit breaker for the radon system, I would put a label there which indicates the system description, the contact name and phone number, and that must be legible from 2 feet. Now, you could also put a central label like this, which is really almost a business card, really. A central label fastened to one of the suction pipes that is centrally located in the basement, perhaps right next to the monitor, because the monitor needs to be put in a visually accessible place, something that you would walk by regularly. And that being the case, perhaps that would be a good place to put the tag as well, the central label. Also note, another requirement on RCP contractors is that system fans are not to be placed in conditioned space, in a basement, or on a crawl space. Now, the reason for that is that if the fan should become damaged or fail in some way, you remember that the radon gas beneath the slab can easily be in the order of hundreds of picocuries per liter. And you're drawing that gas up through the fan and outside the house. If the fan should break or if one of the collars should come loose, then what you're actually be doing is drawing off hundreds of picocuries per liter of radon gas and dumping them, say, in a crawl space directly beneath the living space. And that's obviously not a good thing to do because that radon will percolate up into the living area. So fundamentally here we see system fans not to be placed in conditioned space, that's heated and air-conditioned space, in the basement or in a crawl space for exactly the reason that I have mentioned. Just a few more requirements on the contractor. The discharge point of the, if you have a subslab mitigation system, the discharge point has to be at least 10 feet above the ground. 10 feet from any potential opening that is less than 2 feet below the exhaust point, 10 feet or more from public or private access, and 10 feet or more from adjacent buildings. Fundamentally, what we're being told here is that wherever the exhaust point is for this radon mitigation system, it's got to be 10 feet away from any place where someone could inhale the exhaust gases. 10 feet is the key number to remember. The only complication to it, as you see here, is that if you're putting it up through the roof, which is typically the way to go, it's to be 10 feet from any potential opening that is less than 2 feet below the exhaust point. So here, if you bring it up through the roof, you should have it exhausting 10 feet away, at least 10 feet away, from even a window that would be 2 feet below this point. If the window's 3 feet below this point, then you can actually have the exhaust point a little bit closer. Still, it needs to be 10 feet away. So fundamentally, 10 feet from anything, including the one complication that it must also be 10 feet from any opening that is within 2 feet of the exhaust point. Okay, I don't think that's too difficult to remember. Another requirement of the RCP program listed here, you must ensure, you are responsible as the mitigator to ensure that the follow-up test is to be done between 24 hours and 30 days from the end of the mitigation installation. That is, you put the mitigation system in, let's say you finish it at 10 o'clock this morning, and you are responsible for seeing that a second test, a post-mitigation test, be performed no sooner than 24 hours from now and no later than 30 days from now. So obviously it's going to be a short-term measurement. The idea being that we want to see if the mitigation system is working. We don't want it done within 24 hours, but because if you were working in a basement, you probably had the windows and doors open, and so the radon may be very low to start with. So we're going to give it a day to let the house come to its equilibrium radon condition. But we don't want to wait more than a month because we want to really tell soon that the mitigation system is in fact working. The mitigator is also required, if you're in the RCP program, to recommend that the follow-up test be done independently. It does not mean that the mitigator cannot do the test. It only means that as the mitigator, I must recommend to the client that now you should do a post-mitigation test, you should have it done, and that it should be done by someone other than me. That's the requirement. And you must also, as the mitigator, recommend retesting every 2 years. You're to tell the homeowner that the mitigation system is working, it's working fine, presumably. It's working fine, and please remember that every 2 years we recommend that you do another radon measurement, just to make sure that it continues to work properly. In the area of worker safety, it's very brief, very short. Fundamentally, in the area of worker safety, it simply indicates that you are to comply with all OSHA standards. That's it. That's the only requirement under worker safety as far as the RCP program is concerned. And one relatively new item is the issue of backdrafting. It is possible when you're using a depressurization system that you could depressurize a basement enough to get the exhaust gases, say from an oil furnace, to be re-entrained right back into the house. That is, you have an oil furnace. Let's imagine we have an oil furnace here. It's working. It takes a lot of air from the basement, draws that into the combustion chamber, ignites it, and then the exhaust gases go up the chimney. But if you depressurize the basement, it is possible for that furnace to draw in air from the room, ignite it in the combustion chamber, and then have that gas brought right back into the basement. And that effect is called backdrafting. And as you see here, the requirement of RCP contractors for backdrafting is that all buildings which use combustion devices and have installed a depressurization system are to be tested for backdrafting immediately upon completion of the installation, and that any backdrafting condition shall be corrected immediately. That's the last of the requirements of the RCP program that I'm going to present to you here. And in effect, now on the very next page you'll see another series of questions dealing just with the RCP program. And then beyond that, there's a sample exam, an array of questions put in the back beyond these last set of questions that you'll see. And what I recommend is this. First, do the questions at the end of this part of the program, that is the Part 7 questions. Check the answers, make sure you have those all right. And then take a break, come back later, maybe a day or two later, and take the sample exam. Look at the answers, convince yourself of all the right answers that you understand, and then you will have done the most from this program in order to prepare yourself, to help prepare yourself for the RMP exam. Certainly wish you the best of luck, and thank you.